Hello, students. A very good morning to all of you. Today, we are going to begin with the sessions on science and technology. But before we begin, I'll just wait for 30 more seconds as I see that some of you are still joining the session. And meanwhile, if the audio is clear, the video is visible, please give me a thumbs up. All right, wonderful. Right. So, today we begin with the sessions on science and technology. Now, in these sessions, first and foremost, let me tell you how exactly are we going to go. So first, we'll discuss a few basics about science and technology, about the strategy for this subject and how you should approach this subject. So this is the first part of the discussion that we'll have, and this perhaps will take the next half an hour or so of our time. And then after that, one by one, we'll begin with all the important areas of science and technology. Now, with respect to how we are going to go, also understand that when it comes to science and technology as a subject, it's a very different subject compared to a lot of other subjects that you have been learning. The way you have to handle the subject, the way you have to approach this subject is going to be very difficult, very different. And at the same time, how the questions come in prelims and the mains examinations are also a bit different as compared to the other subjects. So that's why we'll also try to understand those aspects of our preparation so that you get a good hand of what exactly is required for science and technology. So let's begin with the session now. First and foremost, to understand the strategy for any subject and not only for science and technology, to understand the strategy for any subject, what you need to understand first and foremost is the syllabus of the subject. And when we look at the syllabus of science and technology here, what we understand is that at prelims and at mains level, when we look at the things, we get a basic hand of what exactly we can expect in this particular examination. But when you look at the prelim syllabus does not really give you anything away. It does not tell you exactly about what you need to prepare for and what kind of questions can you expect in your papers. So, for example, when you look at the prelim syllabus, there's only one thing that has been mentioned by UPSC, and that is general science. So they've just mentioned general science. Now, how general is that general science? Nobody knows, right? So that's why we don't really get a hint of what we should expect in this paper. At the same time, there is one more point that I have added from my end, and this is the current events of national and international importance. Because when you look at the paper of science and technology, especially when it comes to the paper of science and technology in your prelims examination, you'll see that a lot of questions that they have asked has been related to current affairs. A lot of current affairs based science questions have been asked in the past papers. So that's why I've added this particular point here. But when you look at the mains syllabus, this is where you get a hint of what exactly you need to prepare for. What kind of questions can you expect in the paper? All these things you get something, uh, in your mains paper. So first and foremost, when it comes to science and technology, the main syllabus, when you look at the first point that they have mentioned is science and technology developments and their applications and effects and in everyday life, meaning how exactly science is affecting our everyday life. What are the various aspects of our lives where science has been a major part, and every new way in which science has started to become a part of our life. So that is what we have to expect here, but it does not really give you an idea about what still to study here. Then if you look at the second point, it says achievement of Indians in science and technology, indigenization of technology, and developing new technology. So these are the three things mentioned. Now, here one point that you should understand is that when they say achievement of Indians in science and technology, what the meaning of this particular term is. Achievement of Indians in science and technology. Now, when we say achievement of Indians, it does not mean that you have to study about scientists or you have to know about the biography of a particular scientist and so on. They will never ask you that question. If at all they have to ask a biography based question, excuse me, then if at all such a question has to come, it will come in your GS paper 1 in history, right? History is about biographies, not science. So if they have to ask a question on science, they will never ask you about a particular scientist, but rather it is about achievement of Indians. For example, Chandrayaan 3 is achievement of Indians. So if they ask a question about Chandrayaan 3, it's all about how the Indian infrastructure in science and technology has fared very well, and how it has created a space for itself in all these areas. So that's why from that perspective you have to look at things, and not from the perspective of an individual scientist. All right. Similarly, it says indigenization of technology. Now, when we say indigenization of technology, in a manner you can say, I mean, just oversimplifying things, we would say it is nothing but localization of technology. All right, localization. So indigenization. So for example, let's say there are so many things that have been developed, maybe some part of the world, and it's something that India uses, right? It's something that India uses. Maybe the technology has been developed in US, maybe it has been developed in Germany, France, somewhere in the world, but in one form or the other, India is also using that technology. So then in that case, when India starts using that technology, modifies it according to the needs of people of India, you would say that it is indigenization of technology. So a lot of, let's say, things related to space technology, a lot of things related to defense technology, a lot of things related to communication technology, and so on. In all these cases, what you'll find is that although a lot of these concepts, a lot of these technologies have been developed somewhere in the world, but still what we see is that India has been using it. So that's why it is called as indigenization of technology. And then of course, developing new technology, any new technology that has become significant for India or at least the world, we can find it as very, very important for your examination. So this is how we have to understand all these aspects. Then still, I mean, the topics have not been mentioned yet, right? But if you look at the third point, this is where you actually get the important points. First and foremost, look at this: awareness in the fields of IT, space, computers, robotics, nanotechnology, biotechnology, and issues related to intellectual property rights. This is where you have been defined that this is what we are going to ask you, correct? So these are the topics. This is what will become the crux of every discussion that we are going to have. So let's look at the topics. Let's look at the topics that we are going to discuss in this particular set. So first and foremost, if you look at the topics, the first two topics are space and energy. Now space and energy, I would say, are perhaps the most important topics for your examination, both from prelims as well as from mains perspective. I think there is nothing that is more important than space technology and energy as chapters, both for your prelims as well as for your mains examination. It's going to play a very, very important role. Now, when it comes to space technology and energy, these are also going to be the biggest chapters. I mean, this is something that is going to take a lot of time. Perhaps the first entire week, we are just going to discuss these two topics only, because these are big chapters. There are a lot of concepts to be discussed. There are a lot of questions that have been asked in the past, and there are a lot of questions that we expect to come in the coming years as well. So that's why these are topics which are of utmost importance, and that's why these are topics also where we'll find that it's going to be very, very crucial for you. Then after that, biotechnology, another chapter, still I would say important for both prelims and mains examination, but not as big a chapter as the first two. Still a very significant chapter, because almost every year question does come from here in prelims and mains examination. Then you have nanotechnology. Now nanotechnology, robotics, all these are topics which are smaller topics, yet have become significant topics, perhaps more important from prelims perspective. All right, same goes for robotics and artificial intelligence as well, that more important from prelims perspective, but does not mean that it's not important from mains perspective and questions won't come in the mains examination. Questions can always come in the mains examination, but what we see is the structure of the chapters are more oriented towards your prelims examination than mains. Then after that, we have IT and communication. Still, I would say another prelims based chapter, but again, something that becomes very significant even from mains perspective. And I'll tell you when we go to that chapter, if at all they have to ask questions, how exactly can they ask a question even in your mains examination from all these areas. Then after that, we have two topics: disease and defense. Now, these are two chapters which, anyway, I mean, they have not been mentioned in your syllabus as such, but it's not that questions don't come from here. Questions do come, and questions would come from here. But largely what we see is that the questions that appear in the examination, they are pretty much current affairs based questions. All right, goes for both. Here also we see that these are more of current affairs based questions, and same goes for defense, that we observe that largely the questions are based on current affairs. So for these two chapters, more than what we are studying in the classroom, what happens in the next 9 to 10 months will be more important for you from examination perspective. And then lastly, when we look at the chapter of intellectual property rights, this is again a chapter where I would say that it's more important for mains examination. But having said that, it's we can't really say that questions won't come in the mains examination, just that the in the prelims examination, just that the orientation of the chapter is more tilted towards the mains examination. All right, so this is a crux of everything that we are going to discuss. This is a crux of all the discussions that we are going to have. And uh, these are the broad topics. I mean, under these there are a lot of things that we are going to discuss. For example, energy as a chapter is not a single chapter, but rather a set of 3 or 4 different chapters that we are going to club together as one single unit of energy. So this is how we are going to discuss in all these areas, and these are the topics which become important for you. Now, when we look at the examination and when we look at how many questions have been asked in the past, what you will see is that from each and every question papers perspective, you will see that on an average 13-14 questions can come here. I mean, we see that every year these many questions have been coming. This year, for example, in 2023, we saw a total of 12 questions, which were 12 direct questions, plus there were a couple of questions which were indirectly also based on science. But what we see is that largely 12 to 13 questions every year have been coming in the prelims examination. And in the mains examination, we see that every year 3 to 4 questions have been coming. Now, when we look at this analysis, understand something, and something that is very, very important from your examinations perspective, and important if you consider clearing the examination from the perspective of prelims examination first. 12-13 questions on an average, sometimes more than that, sometimes 15-16 questions also have been coming. Now, when we look at this trend, what we also realize is that this becomes an important topic. This becomes an important area, because look at 2023 question paper. And I don't have anything against any other subject, but I'm just telling you about the return on investment that you get in these kind of subjects. Subject like science and technology, you don't really have to give it a lot of time. First of all, we have how much? I think 11 classes we have in total. That will be enough for you to cover everything, plus current affairs that you'll keep covering anyway throughout the year. And that's enough for you to get 12-13 questions. If I compare this to another subject, let's say if I ask you, if you look at the question paper of 2023 and tell me how many questions have come from history, you'll see that almost there are 20 questions. Let's say there are a total of 20 questions or 18 to 20 questions that have come. Now, in all these sessions, what we see is, I mean, for history, you have ancient history, medieval history, modern history, art and culture, post independence, and let's leave aside world history because questions don't come in your prelims examination. So you have, I would say, in a manner, you have almost 4.5 subjects, and that is bringing you somewhere around 17 questions, where you have this one small subject which is bringing you 12 to 13 questions. So then think about the return on investment. Think about how many questions and in how less a time does science and technology give you. And this is where we see that a lot of students, a lot of aspirants also falter. And I'm just being very blunt here. What I've seen is that this is one area, along with probably also environment and ecology, that these are areas which are very easily neglected by the aspirants. That your focus always is on polity, economy, geography, and perhaps modern history. These 4 subjects you probably take one whole year to complete. Everybody will tell you that these are the big four. Yes, I agree, these are the big four, but largely in the mains examination, not in prelims. Because when you look at prelims, you'll find that each and every subject, there is no guarantee how many questions will come from what subject. Go back to 2013 and 2014 question papers, you'll find that there is one year where more than 30 questions have come from environment and ecology, one of the most widely neglected areas of your syllabus. And look at question papers of 2018, 2019, you'll find that not even 10 questions have come from geography, something that is such a vast syllabus, had not even 10 questions, and that too 2 3 questions based on current affairs. So you would have given probably 2 or 3 months of your time to just studying geography, maybe more than that. And unfortunately what I've seen is many people, and many, I mean, from uh, this coaching industry, many people also say that leave science. What happens, there are 10 questions that will come from science, don't study science if you don't find it easy. It's a wrong thing to even imagine that. Are you so sure that out of 80 questions you are going to solve 70 questions correctly, you are going to do very well in all those 70 questions? You can't really guarantee that. So many a times we see that I mean, not only about science, something will also be said about something like, let's say, medieval history, that no need to go through medieval history, just see that there are 2 or 3 questions that are coming, so you can leave out those 2 3 questions. Has UPSC told you ever that they are only going to ask you 2 or 3 questions from medieval history? Or has UPSC told you that they will ask only 8 to 10 questions from science? No, not at all. It just says that there are a total of 100 questions that will come in your GS paper. That's it. The distribution, nobody knows. There has been a year, for example, in polity where 22 questions came just from polity, and the very next year there were 12 questions from polity. 2016-17 paper, there were 66 questions that were somewhere based on current affairs. In one way or the other, it was based on current affairs. Next year, there were 18 to 20 questions based on current affairs. So what happened? That as soon as 66 questions came from current affairs, every aspirant next year was just studying current affairs, thinking that if you do current affairs very well, you'll clear the paper. So just remember this. There's no guarantee that what area will have how many questions. Tomorrow, perhaps I'm saying all this and only 2 questions come from science, or maybe 20 questions come from science. There's no guarantee about that. So that's why you always have to understand that every subject in your syllabus has some kind of weightage. It is going to be important for you in one way or the other, and that's why you cannot neglect, especially a subject like this can't be neglected. A subject which is going to have as many as 15 questions can't be neglected, and you can't really go blind on these kind of subjects in your examination. And I'm saying, stressing on this point mainly because I have seen how a lot of times wrong analysis has been given, a wrong strategy has been given, and that costs the aspirants dearly more than anyone else. So that's why, just remember this. Long story short, that anything that has been mentioned in your syllabus can't be neglected. You can't go on a past paper and say that in future also something similar is going to happen. So it is always going to change, and you cannot really predict what's in the store for the next year's paper. You have to be exam proof, you have to be pattern proof, you have to prepare for your syllabus. If your syllabus is done, you can be guaranteed that you'll be able to do very well in the examination. But you cannot go on a hunch. You cannot go that, okay, look at 2021 and 22 and 23 papers, so this is what will happen in 2024. You can't guarantee that. So that's why you have to be very, very uh, mindful of all these things. Coming to the trend that we see in the mains examination, we see that every year 3 to 4 questions have been coming. Now, about these 3 4 questions, so in a manner you can say that 35 to 50 marks is what we can score from this particular area. Now, these questions, I mean, the number is insignificant. I would say that science in mains examination is not as significant for you as in the prelims examination, for two reasons. One, there are only 3 or 4 questions coming from here, whereas from polity you would have more than 10, history you would have more than 10 12, economy you would have 10 12, geography will have a significant number. Compared to that, there are only 3 4 questions coming from here, but these are easy questions. We'll also look at the past papers, we'll also look at the some of the questions that have come in the past, and you'll see that these are easy questions. These 3 4 questions are not very difficult to answer, and it very easily can give you a good amount of marks in your GS paper 3. So, and we'll take those examples, we'll see those past papers, and you'll also get a hang of how exactly the questions have been coming. But what I'm saying here is just understand this, that these kind of subjects, they cannot be taken for granted. You cannot just think that you'll just leave something and it will work out for you. It's a very big risk to take if you're really doing that. Now, coming to the strategy and thing of how exactly the questions have been coming and what are the key areas from where we see the questions in your paper. So there are few things. First and foremost, all the major scientific breakthroughs and the major running stories in the field of science and technology. Now, one thing I would tell you, that if you go back to the past papers and you see what kind of questions have been coming and where the questions are being picked from, you'll always find that questions that are being picked, the questions are being picked in a manner that they have some kind of significance. They have some kind of significance from the perspective of your prelims, or some kind of significance from perspective of India, or at least it's something which is important for the scientific world in general. Something which is very insignificant will never be asked. Now, how to identify this, that what is significant and what is not significant? So anything that is significant, first of all, anything that is significant perhaps will not be run in your newspapers or your articles only once. It will reappear. It will come maybe once in a month, maybe 2 or 3 months later, you'll find the same news article again, or something related to the same topic again, and all these things will keep on happening. So that is a hint for you that this is an important topic, because it has reappeared in your paper. All right. So something that has reappeared, we understand that this is an important topic. Similarly, at the same time, how to identify what is not important. Many times what you'll see is that, especially for example, let's say if you're following the Hindu or if you're following the Indian Express, you'll find that there are some articles which just are research based articles. The question or the article will go something like this, that recently according to scientists at this university, recently due according to a research done by this and that, you'll see that this is how they would start talking about certain topics or certain articles. In all those kind of areas, just understand that these are not important. Why am I saying this? That the reason is that there are so many researches happening all across the world, and there are so many research institutes, there are so many companies and firms that are doing the research, there are so many universities who are doing the research, there are so many people all across the world who are just doing their PhDs, and yes, they are doing that research for their PhD. So just imagine, I mean, in your city, how many such universities or maybe colleges you have where some kind of PhD is being given, is being done by the students there. Just multiply this by the number of districts that we have in India, and multiply that number with the number of countries that you have in the world. So just imagine the amount of research that is happening day in and day out. There are so many science journals like Nature or Science or anything like that, Scientific American. So there are so many such research journals, and they will keep on publishing all these articles. What the newspapers will pick up would be something that is interesting. So newspaper is not all only for for a UPSC aspirant, right? It's not that the Hindu is not read by anyone else but only the UPSC aspirants, correct? So they have to cater to all their audience, correct? So that's why you cannot really you cannot go by that logic. So that's why just understand this, that it is a small article talking about some kind of research that happened somewhere. You can neglect that. But something that is a breakthrough, something which is new, something that is never seen before, and these kind of things that keep on reappearing in the paper, or maybe has appeared in multiple newspapers, then it gives you a hint that it's going to be important. And not only those stories, but also the static areas of those topics. So the basic concept behind that topic, the basic concept behind that story, they'll ask you questions from there, and I'll show you examples. I'll show you examples of how in the past papers something like this has happened, and almost every time it happens. So that's why it is going to be important. Then government programs and initiatives, something which is always important, goes without saying, not only for science and technology but every other subject as well. And then lastly, consumer oriented technology. Now what we have seen is that in the past papers, UPSC has been putting a special emphasis on something which is or technology or science that is related to consumers. Wearable technology like your smartwatches, Bluetooth devices, and so on. A question has been asked on that. LEDs, number of questions have been asked. 3G and 4G question has been asked. Then Internet of Things questions have been asked. OLED question has been asked. So there are so many things on which questions have been asked in the past. Something where we see that this is uh, this is uh, uh, a consumer-oriented technology. A good example in our present scenario is 5G. 5G is a consumer oriented technology. Until now, they have not asked a question based on 5G. So, in the coming papers, we can assume that this is going to be a very, very important topic for us. So, in this manner, anything that is related to consumer and has been in discussions, you can expect that questions can come from all these areas. So, that's why you have to identify these areas as well. That whenever you look at current affairs, whenever you're reading current affairs, these are some of the key areas that you should always focus on. Now, lastly, what are our sources? Sources, first of all, the key source would be a newspaper. The newspaper, you can pick any one, either you read the Hindu or the Indian Express. Just remember that there are two newspapers. One is the Indian Express and one is the New Indian Express. What I am suggesting is the Indian Express. So just know this. All right. Because Indian Express has a wider circulation in the north and lesser circulation in the south. And New Indian Express has more circulation in the south and less in the north. So that's why just be aware of this point, that we are talking about Indian Express or the Hindu. Any one of the two can be picked. If you can read both, great. But even if not, at least one of the two should be read. Then the second good source is PIB. What is PIB? Press Information Bureau. What is the significance of Press Information Bureau? We get, you can say in a manner, every new scheme, every new program, every new policy of the government will be there on PIB, will be always there on PIB. So that's why PIB becomes a very, very important source for you for everything new that the government of India is doing. All right. So that's why it becomes a very, very important source. And again, not only for science and technology, but any other subject as well. See, what you can do is, and I'll tell you about this, that PIB, if you go to PIB website, or PIB also has an app. If you go there, you can select the ministry, you can select the date, you can select the year, you can select the month, and you can read everything that is there. And you'll find some important articles you can read from there. Then after that, the magazines. Science Reporter, Down to Earth, Yojana, and Kurukshetra. Now, these magazines, I wouldn't suggest that you should read it from cover to cover. Especially, let's say something like Science Reporter should not be read from cover to cover, because it's a very technical magazine. It's not very easy to follow this magazine, for especially for somebody who doesn't come from a tech background. So it can be very, very difficult for you. So that's why I would not suggest that you read it on your own. You read it from cover to cover. And even when it comes to Yojana or Kurukshetra, or even these two, uh, all these, they always have to be read selectively. So you have to read these selectively. Now, about the newspapers, PIB, all these magazines, what I would suggest is that if even if you can't read everything else, or if you do not have the time, or even if you have the time, follow everything that we are doing. The Daily Hindu analysis, the CNAs that are being given to you, the PIB analysis that is being given to you, the webinars that are being conducted for you, the monthly magazines that are being given to you, all these sources, they are covering everything. They are covering the crux of each and every important article that we have in all these areas. So you do not have to go through each and every article, try to identify what to read, what not to read, and all these exercises you don't have to do. Instead, you just follow everything that we are giving you. You can simply go on your Byju's exam prep app, and on Byju's exam prep app, you'll find that the Hindu analysis is placed there, the daily news analysis is placed there, the PIB analysis, the comprehensive news analysis is placed there, the webinars are being conducted there for you. So you can just follow the Byju's exam prep as your one source for all the current affairs requirements. So instead of going to each and every source, I would suggest that this is one of the ways you can follow everything. All right. But when it comes to the newspapers, what I would still suggest is that if it is possible for you, if you have that time, try doing this exercise, that go through the analysis that we are doing, and after that also read the article on your own. But after the analysis, after watching the analysis, read the article on your own. It will really help you. It will help you not only in understanding the topic, but also develop that language, develop that academic language that you need when you are writing your answer, or when you are doing something of your practice. It will really help you subconsciously develop that language. So that's why my suggestion would be that, let's say for example at 10 o'clock the daily Hindu analysis happens, right? It happens live. So follow that, and after that, after you have done that, just try reading that article that was discussed in the analysis on your own, because now you only already know the context, now you already know the story. So reading this article for you will be easier now. But as you read on your own, you are also working on your own, you are also spending some time here in building this. It will also help you a lot. If you don't have the time, then only follow the analysis. But if you do have the time, I would still suggest that you should also read on your own after watching the analysis. Then lastly, the NCRTs. Now when it comes to the NCRTs, what I would suggest is go through class 6 to 8th NCRTs. Class 6 to 8th NCRTs, and from the perspective of class 9 and 10. From the perspective of classes 9 and 10, there are few chapters that I would suggest that one should go through. There is a chapter on force and laws of motion. So this is one chapter that can be read. Then there is one chapter on gravitation. So these two physics oriented chapters can be read. Then from chemistry perspective, there is a chapter on structure of atom. So I would suggest that you should read this chapter. And then from biology perspective, there is one chapter called as fundamental unit of life. Fundamental unit of life, which is basically about the cells that we have in our body. And then there are a couple of chapters which are related to the human body and the various systems and organizations that we have in the human body. So from class 9th and 10th perspective, only this much also if you study, it's more than enough. And largely I would suggest that class 6 to 8th NCRTs should be studied to give you a base on in science and technology. Because having said everything, this, if you see, all these are just current affairs sources, and these are some basic sources. NCRTs are your basics, and everything else is your current affairs source. Now what I want you to do largely is to depend on these classes. What we are going to do in the next 11 sessions, just focus on this. Do everything that we are discussing in the classroom, all the notes that we are giving you in the classroom, the annotated PPTs, the lectures, the additional notes, that's it. And then current affairs. Nothing else is required. All right. No need to go to any extra source, no need to go to any other book, any textbook whatsoever. Nothing else is required. Just do this, that whatever we are doing in the classroom plus current affairs will solve all the problems for you, and that will be it for what's required in this examination. Because science and technology is a very different subject compared to many other subjects. So the way that you approach other subjects is not how we would approach this particular subject. So that's why this is what I want you to do, that only focus on this, focus on whatever we are doing in the classroom, plus add current affairs to this. That's it. If you have done this much, it will be more than enough for you, and you will be well prepared for your examination. So, and even in a difficult paper, in a difficult examination also, I can tell you that very easily more than 60-70% of the paper, of the questions will very easily come from whatever we are discussing. Even in a difficult paper like 2023 prelims paper was a very difficult paper, and you might have seen the analysis everywhere by now. Even if you have not, you would see this, that this was a very difficult paper. But having said that this was a difficult paper, 10 out of 12 questions in science and technology came only from what we had discussed in the classroom. Even then, even with a difficult question paper, it happened. So that's why I'm saying that just focus on what I'm telling you for this class, plus the current affairs sources. That will be it. Nothing else is required. All right. So this is a basic of what we need to do. Before we begin with the first chapter, if you have any doubts, please let me know. If you want to ask something, please let me know, and then we shall start with our discussion. How many modules are there? There are total of 11 modules that we are going to follow. More than modules, just think of chapters. All these are chapters that we have. Science and technology is only part of the mains. No, no. Prelims and mains, this is what I told you. AI is not a part of our syllabus. See, it has not been mentioned in the syllabus, but of course, as a chapter, we'll have to take artificial intelligence, perhaps one of the most important topics in today's day and world. So, can't be neglected. So, as a chapter, we'll have a discussion on artificial intelligence as well. How to make static notes of the class and how to add current affairs to that. So, see, static notes will be dependent on what we are discussing in the classroom. Everything, see, a lot of information I've already included in the PPT. Whatever extra information is required, I'll keep writing that down so that you have a holistic view of every chapter. So you can keep following these notes only. And then current affairs should be done topic wise. I mean, current affairs always try to add to the required topic. So if you, let's say, see something related to biotechnology, try to add it to the relevant topic in biotechnology chapter. So this is how you should do it. Where can I find the gist of Yojana in Byju's? You can simply go to the Byju's exam prep app, and there on the home page itself, you'll find that all this analysis has been done. Is there no need of reading Byju's book of science and technology? I would still say it's not required. I mean, any book is not required here. We I mean, this is a chapter, sorry, this is a subject which is very different, and books don't really help directly. So even if you skip the book, doesn't matter. Even if you don't read the book, doesn't matter. I mean, I would rather spend time on reading current affairs than reading the book. So that's why I said classes plus current affairs. That's it. My attempt is in 2026, so how should I approach this subject? See, for 2026, whatever we are doing in the classroom, that will basically make the base for you, and this is all the areas that are required from static perspective. Now for current affairs, what I would suggest is that just 15 months before your paper, let's say if it is happening in June 2026, then March 2025 you should also start looking at current affairs. Right now, even if you don't study current affairs, it will not really matter for you. You should just know the very very big stories. For example, Chandrayaan 3 is a very very big story, so you should know that. But apart from that, smaller topics you can neglect. That, for example, uh, uh, ISRO's new space policy of 2023, for now you can neglect it, because by then a new space policy would have come, so it will not be relevant for you. So that's why this is how you have to see this. Instead of NCRTs, can I only read Baiju's book? Is it sufficient or not? I would suggest still NCRT. See, NCRT, especially class 6 to 8, they really make the base for you. because what I mean, when you revisit the NCRTs, you'll find the beauty in NCRTs now. Because what happens largely is that when we are in school, our approach towards these subjects and these books is pretty different. We largely just remember everything. We just try to learn everything, and we just go. Conceptually, we perhaps are not really aware of concepts many a times. So that's why uh, I would still suggest class 6 to 8 NCRTs hardly takes any time. I mean, class 6 and 7 can be read very quickly. Within a day, you'll be able to complete them. Class 8 might take a couple of days. That's enough. So just do this much. So I would still strongly suggest that NCRT should be read. Whether you are from science or non-science background doesn't matter. I would still suggest that you should read it. Can I print out PPTs and add notes? Even if you don't print it out, doesn't matter. I mean, you can add digital notes to it. So that would also be helpful for you. Running notes are important to make. See, depends on you. I mean, when it comes to notes, just understand it. And okay, this is for every one of you, that when we talk about the notes, understand the significance of notes. That okay, fine. Let me ask you this: that if I ask you, why do we make notes? All right, answer this question: why do we make notes? Yes, so many of you are writing revision, correct? But yeah, so what Nitish you have written or Prince you have written, fast revision, quick revision, right? Easy revision, Janvi, as you have mentioned. Yeah, easy, yeah, to revise easily, Aniket, you have mentioned. So you understand the crux, correct? That why do you make notes? You make your notes for yourself, correct? You make notes for yourself. So you have to make notes. I mean, whatever you do. See, there are many approaches here. All right, there are many approaches, and I can't say that this approach is correct or that approach is correct. You follow only my approach or you follow only your approach. No, every approach is individual to an aspirant. So, for example, many of you might want running notes, that you always keep taking notes as we speak, as we teach something. That's good. It's your habit. So, it's fine. It suits you. Many of you would completely depend on every note that we are giving, the annotated PPTs and the additional reading material and so on. Great. It works for you. So, just understand this. Whatever works for you is the best strategy. You cannot force yourself to towards a certain strategy, and if it doesn't work for you, it doesn't matter. Because many a times what happens is, for example, let's say as an exercise, just go and see what the toppers have been speaking about. You'll find so many YouTube videos of so many different toppers of last 4 5 years. You'll find that there are those videos on YouTube, some many of them on our channel, many of them on other channels. So you just go there and you'll see that each and every aspirant, each and every topper also talks about a different strategy. But so just understand this: the best strategy is the strategy that works for you. So same goes for making notes as well. Understand the crux. Why do we make notes? We make notes for ourselves. We make notes so that we can revise it better. We can revise it later in an easier manner. We can do a quick revision and an easy revision. That is why we make notes. So you always have to keep that in mind. Many times what happens is that while we are making notes, we also become we also divert from our consciousness. So what then happens is that we keep on making very big notes. That doesn't help. You can't really write down each and everything that I am saying or each and everything that the book has written, because then it will be as good as watching the entire video again or reading the entire book again. You have to make a crux out of it. So that is something that you should always remember when it comes to making the notes. I want to take printout, but I'm confused. Shall I print the class notes or additional reading material? See, ARMs can be printed out, and you can probably keep on adding your current affairs to that, and keep a digital copy of the annotated PPTs with you, so that both can be used simultaneously. Is it live or recorded? Of course it is live. It's not recorded. Recorded sessions will be available to you after the class. Right? So I think NCRT book names, please. NCRT books, I mean, the books are called as general science books. You can even go to NCRT website and you can download the books from there. If you go to ncrt.nic.in, you'll find that there is a part called as publication. You click on publication, you'll see that class 1 to 12th is written there. You click there and you'll find that class wise, subject wise, all the books are also available there. You can download individual chapters if you want. You can download the entire book if you want. All those options are there on the NCRT website itself. How to make digital notes? I mean, for making digital notes, there are a couple of ways. Either, if let's say if you have a tablet or something, a writing tablet or something, you can make notes there as well. Or if not, you have things like Evernote, etc., which will also help you collate the notes, so that also can be used. Is it available online? Science Reporter is available online, but I think they are not freely available. I think they charge for it. The older issues are available for free. The newer editions are actually available with a charge. Roshan, it's not a recorded session. I hope I clear your doubt now that I've taken your name and I've told you that this is a live session, not a recorded session. Why would we play a recorded session 6 o'clock in the morning? All right. So, all right. Some of you have asked for my, yeah, e-app is also there, correct? With the name e-Pathshala, you're correct. So e-Pathshala is also a very good app if you want to download. There also you will get all these books. Right. So many of you have asked for the email ID. So if you have any doubts, if you want to ask anything further, you can always reach to me at rasesh.kumar@byju's.com. This is my email ID. So you can note it down, and if you need it, if you want to ask any question, you can always send me your questions on this email ID as well. Right. So this is about the first part. This is about, okay, so one more question. Do questions come from NCRTs? Is it only for building concepts? It's more for building concepts. Hardly any questions come from NCRTs. This year it was zero. Last year it was zero. Before that there was one question. So every 3-4 years, just one question appears, and that too pretty general question, which anyway without reading the NCRT also can be answered. So that's why uh, uh, NCRTs are more for your basics, and the basics are very very important. I'll tell you why. Achha, first thing, what I also want to understand from your perspective is, how many of you are from science background, commerce background, and arts background? Just mark A, B, or C for science, commerce, and arts. I'm just launching a poll for you. I just wanted to understand this. I mean, there are no right or wrong answers, but I have to, it goes by default. Please let me know. Please mark here so that I also get an understanding of what is the student base here. Okay, so a lot of you from science background, and then from commerce, and then from arts. All right. So arts background also has a significant number here. Good to see. Now understand this, that what I just asked doesn't matter. That whether you are from science background or from arts background or commerce background does not really matter, because I see that a lot of times students always think about, okay, if I'm from science background, history will be difficult for me. If I'm from arts background, science will be difficult for me. There's nothing like that. each and every subject is equally difficult and equally easy. So there is nothing, you have to just be here with a clear mind. Yes, there are certain areas that can be somewhat technical for people who come from non tech background, but I can guarantee the same will happen to the students who are coming from tech background as well, that they'll also find those topics difficult, because there are topics like nanotechnology that even if you are from science background, you would have hardly studied anything about nanotechnology, or anything about, let's say, artificial intelligence. You would have hardly, there would be very few of you who would have actually done something great with artificial intelligence. So that is what happens here, that every subject is, or every topic in science and technology is so different that even if you come from that background does not really matter. And as an exercise, I always do this in every first class that I take. If I ask you how many organs are there in the human body, I'll give you four options: 1 to 50, 51 to 100, 101 to 150, more than 150. Let's say these are the four options that have been given to you. Launching the poll, quickly mark your answers. Wonderful, Amrit, Ashish, Anshika, you have given the perfect answer. So, see, this is where the problem lies. 37% of you have marked A, 30% of you have marked B, 11% of you have marked C, and 22% of you have marked D. Now, just think about this organ, the word organ. I'm very sure that every one of you have heard this term, that there is something called as an organ in our body. You know this much, right? You don't know this much, that there is something called as an organ in our body. And the first time you might have heard this term organ perhaps would have been in your class 4th or 5th or somewhere around that time. Yet after even completing class 12th, and perhaps many of you have completed your graduation and all also, and yet when I ask you number of organs in our body, we are still confused. This is what happens. Uh, this is why we have to understand that the things are very different at this level of UPSC. Conceptual understanding becomes very, very crucial, because the correct answer, for first of all, I'll tell you the correct answer is 51 to 100, because there are 78 organs, 79 and 80th organ are under right now observation, that there are two more organs that they might add to the list of organs that we have, so the number might become 80. So now what happens is that, first and foremost, what is an organ? An organ, you can say that it's a set of tissues that does a specific function in our body. So any set of tissues in our body that does a specific function will be called as an organ, and that's why the number of organs will be limited. It will not be a very high number. So so now what happens is that, because these are very basic things and we are not really aware, because the way we have been studying for a very long time has been very different from compared to what we have to do now. So that's why I understand this, that why I'm saying that whether you are from science or non-science or commerce or arts background doesn't really matter. For everyone, everything that we are doing is going to be equally important and equally easy or difficult. For some maybe more, some maybe less, but more or less everybody of you will be at the same level. And if you have any doubts, if you don't understand anything, you always have us. You can keep asking your questions and we'll keep taking those questions. All right, so let's start with the first chapter. The first chapter is space technology. Now, when it comes to space technology as a chapter, this is a chapter, first and foremost, which, as I told you, is very, very important from both prelims and mains perspective. And without any exception, you will find that prelims every year, at least one question comes, if not more. And in the mains question, mains paper also, uh, almost every year one question does come. Only in the COVID years 2020 and 2021 we have seen that the question was not asked from space technology. But before and after that, I mean 2022 also one question came, and 2019, 18, 17, 16, 15, 14, if you keep going back, you'll find that each and every year at least one question has come from science and technology, even in the mains examination. So that's why space technology becomes the most crucial chapter from both prelims and mains perspective, not only because of what we have observed in the pattern, but also because of the importance that this subject has, the amount of interest that this topic generates in people every year, all across the world. Just look at Chandrayaan 3 and how excited everybody has been about Chandrayaan 3, that there were so many people. I mean, what was the view? I think there were 80 million views on the ISRO YouTube channel, people watching it live. So just imagine that the kind of interest that it generates. I had an evening batch with the Hindi medium students then. I also had given a 10-minute break back then, and I just went on to just see I mean, the landing happening live. So the kind of interest, and not only me, I mean, even the students said that please give a break for 10 minutes so that we can see that landing on the moon happen. So we understand the kind of interest that space technology in general always instigates. Because of that also, there are so many new things that we always keep seeing. There are so many new aspects that we always keep coming across, and every day there will be something new that we keep on finding. Some new image of something that we have never observed in the space always keeps on happening, and that generates a lot of interest in the minds of everyone about space science. So that's why space technology, from that perspective, that's why I'm saying that it's not only about what we have observed in the past papers and the pattern, but rather in general what this topic is about, and how interesting this topic always has been for everyone across the globe. And that's why we see that this becomes a very, very crucial topic. Now, how we'll approach this chapter? There are two parts into which I've divided this chapter. The first part will be of space science. All right, the first part will be space science, where we'll understand the universe, the various aspects of the universe, and everything related to it. And then the second part will be space technology, where we'll discuss about a lot of things related to the satellites and how we launch the satellites and why we launch the satellites, what are the applications, what are PSLVs, what are GSLVs, and what is ISRO, and all these kind of things will be the second part of our discussion. All right, so let's begin. The first thing in space technology, we'll try understanding what the universe means. Now, if I ask you to define the universe, this is going to be a difficult task, because how do you define something that is indefinable? Because it is something, I mean, we know about the universe, that universe is everywhere. We perhaps can say that there is nothing outside the universe. So when there is something that you cannot really bind in its boundaries, how do you define it? So a very simple way to define, a very philosophical way to define: everything that exists, everything that has existed, and everything that will exist is a part of the universe. All right. Now, why are we saying this? Everything exists, everything that exists is fine. Okay, fine. I understand that everything that exists is a part of the universe. But why we are still saying that everything that existed and everything that will exist is also a part of the universe? A simple way to explain this is something that I'm sure you have heard of: law of conservation of energy. Heard of it? Law of conservation of energy. What do we say in law of conservation of energy? It is what do we say? That energy can neither be created nor destroyed. It can only be transformed from one form to another. Meaning that you cannot create new energy, you cannot destroy energy, you can only transform energy from one form to another. Correct? And from there we also derive law of conservation of mass. Correct? We also define law of conservation of mass. So law of conservation of mass also says something similar, but more important is law of conservation of energy, and how law of conservation of energy talks about things. So what we say is that energy can neither be created nor destroyed, it can only be transformed from one form to another. Correct? So that's why we are talking about everything that existed and everything that will exist. Because anything that exists in one form today will exist in another form tomorrow, will take another form after that, would have taken another form before this. So that's why these forms keep on changing. But what is significant here is that there is a continuous change or modification that keeps on happening. It doesn't get destroyed, it doesn't get created. That is what we say. So that's why everything that exists, will exist, and has existed, everything is a part of the universe. So that's why, for example, let's say a star that is shining very bright today will die someday. And when it dies, it will just, I mean, release a lot of gases and a lot of particles, etc., which will perhaps become a nebula maybe, or become something else. So it is just a transformation that has happened, and it's not that it completely lost everything. Correct. So that's why law of conservation of energy in a manner defines this. Now, the complexity of the understanding of the universe starts when we look at the composition of the universe. So, when you look at the composition of the universe, what you see is that there are three parts to it: dark energy, dark matter, and the rest. Where we see that almost 70% is dark energy, almost 25% is dark matter, and only 5% is the rest. So, to be exact, it is said to be 68%. 68%, and this is 27%. So these two together make up 95% of the universe, and the rest is 5%. So let me first start with the rest, and let me then go to dark energy and dark matter. So the rest, when you look at the distribution of the rest, you see that 4% of the rest is just hydrogen and helium. 4% of the rest is just free hydrogen and helium. All right. Then comes 1%. Okay, can you see hydrogen and helium? You can't. So 4% of the entire universe, 4% of the entire observable universe is just hydrogen and helium. And then coming to the last 1%, out of this 1%, 0.5% are all the stars in this universe. All right. All the stars in the universe together, they are just 0.5%. So billions and billions and billions and billions of stars together, 0.5%. How much do you see out of it? If you're living in, let's say, a bigger city or a metro, perhaps 10, 15, 20. If you're living somewhere far off, maybe 50, 100, that's it. Correct? So it's, and you can say almost a very, very, very tiny fraction of what exists out there, right? So that's why this even 0.5%, only a very, very, very tiny fraction of this 0.5% is what we see. So these are all the stars. Then 0.3% are neutrinos. Now understand what we mean by the neutrinos. So neutrinos, they are chargeless, and let me say almost massless. Right. So these are chargeless and almost massless particles. Now chargeless meaning that they neither have a positive or a negative charge. For example, you might know that electrons have negative charges and protons have positive charges. So here it's neither positive nor negative. All right. So that's why we are saying that these are chargeless particles and almost massless particles. So why we are saying that these are almost massless particles? Because the mass is very, very low. Mass of a neutrino is almost negligible, one of the lightest particles that we know of. So even compared to, for example, let's say something like a proton or a neutron, which is heavy, compared to that, electrons are lighter. But even compared to even compared to electrons also, we see that neutrinos are even lighter in their mass. So that's why mass of neutrinos, we are saying that these are almost massless particles. All right, almost massless particles, because mass of neutrinos are very, very less. Now now when it comes to neutrinos, understand that neutrinos basically are particles. Neutrinos are particles which are found naturally in the entire universe in a very tiny fraction, as you can see, only 0.3%. But there are some natural phenomena that lead to the production of these neutrinos. So for example, so if we are talking about the source, the source of neutrinos, first source can be something called as supernova. We'll discuss what supernova is. Then nuclear fusion that is happening in the stars. So in all these cases, we see that these become sources of neutrinos being released, and they are being released in significant number, because 0.3 in the context of the universe that we know of is a big number. Then after that, if you see the next part, this 0.17% is antimatter and electromagnetic radiation. Antimatter and electromagnetic radiations. Now, antimatter and electromagnetic radiations, we'll discuss more about electromagnetic radiations when we go to IT and communication chapter. We'll have a detailed discussion about them there. But you know that, for example, visible light is an electromagnetic radiation. The radio waves on which our mobile phones are based, they are radioactive, they are electromagnetic radiations. uh, the radiations that are emitted by the radioactive elements like gamma rays, for example, they are electromagnetic radiations. So more about that we'll discuss later. Now, what is antimatter? All right, what is antimatter? So antimatter, understand what antimatter means. So antimatter is where you have any kind of particle with same mass and opposite charge. Same mass and opposite charge. So if I ask you, are electrons and protons are antimatter of each other? Are electrons and protons antimatter of each other? Yeah, so many of you have said no, some of you have also said yes. But yes, Deepika, you have mentioned it correctly. Abhishek, you are correct. Amrit, you are correct. Saloni, you are correct. So you understand this, right? So what we are basically saying is that antimatter with same, they have same mass and opposite charge. Now protons are almost 2000 times heavier than electrons. So that's why protons cannot be called as the antimatter of electrons. Antimatter of electrons are particles called as positrons. So you have electrons and you have positrons. So positrons can be called as antimatter of electrons. Protons cannot be called as antimatter of electrons because protons are much heavier compared to the uh, electrons, right? So this is basically what we see. This is how we understand the things. So now antimatter and electromagnetic radiations also make up almost 0.17% of the universe. Then lastly, coming to this small part of 0.03%. So this 0.03%, we are saying that these are heavy elements. Now understand what we mean by heavy elements here, because the definition of heavy elements in terms of astrophysics or in space technology is different. Because in general, if I'm saying heavy elements, you might think that okay, this is something which has a high atomic number or a high mass number and so on. But here, no. When we say heavy element, for us, heavy element here means every element apart from hydrogen and helium. All right, every element apart from hydrogen and helium, they can be called as heavy elements. So that's why here the definition of heavy element is different, because hydrogen and helium we have already accounted for in this 4%, and in the rest 1%, only 0.03% are all the other elements in the universe. So just imagine that everything that you actually see on the earth is just making a very, very, very tiny fraction of the entire universe. So this is how the composition of the rest 5% is. This rest 5% is the part that we know of, the part that we can observe, the part we can understand. Then comes the problematic parts. The problematic parts are dark energy and dark matter. So just try to understand what we mean by dark energy and dark matter. We understand the rest. We understand the distribution of the rest, that you have 4% of hydrogen and helium, 5% of all the stars in the universe, 0.3% of all the neutrinos in the universe. Then after that, you have 0.17% of antimatter and electromagnetic radiation, and 0.03% of all the other elements apart from hydrogen and helium. So all these are, this is how the composition of the rest 5% is. Correct. Coming to the 95%, the 95% part is dark energy and dark matter. Now, what do we mean by dark energy? Are there any kind of dark forces behind it? Is there a super villain that is guiding this energy? No. Dark energy, why we are saying that this is dark energy? The reason is simple. We don't know. We don't know what kind of energy it is. We have no idea about what kind of energy it is. We are in the darkness. We are in the darkness. We don't know what kind of energy it is. So we named it as dark energy. Now, same goes for dark matter as well, that it is a kind of matter that we think exists, but we have never seen it. So we are in the darkness, we don't know about them, so we named it as dark matter. All right. So until now, this is the story. Until now, this is the story, that dark energy is the kind of energy that is there in the universe, but we don't know in what form. We don't know what kind of energy it is. We are in complete darkness, so we named it as dark energy. Now, if we don't know what kind of energy it is, how do we even know that it exists? How do we know that an energy like this exists if we don't even know what kind of energy it is? Understand this, that how exactly do we know about dark energy? And this needs some context, some history about our understanding of the universe, because what we see is that our understanding of the universe today is pretty different from what it used to be. So first, for example, there is something called what initially what we always thought was that the universe always remains static, meaning that, let's say, if these are three galaxies, you have three galaxies A, B, and C, then in time this A, B, and C will remain as it is. Even in lakhs of years, it will remain as it is. All right. So now what we understand, so this is the early understanding of the universe, that what we understood, what we thought was that in the universe always remains in a static phase, it always remains like this. So this was also called as steady state theory. All right, this was called as steady state theory. So this was the early, this you can say in a manner was an early understanding of our universe. Then came a scientist whose discussions we'll keep doing every chapter, Albert Einstein. Now, Albert Einstein, he was working on his theory of relativity. And in his theory of relativity, the calculations that he had done, his calculations showed that the universe should not be in a steady state, but rather the universe should be expanding. His calculations showed this, that the universe should be expanding. But he was also a firm believer of the steady state theory. He thought that he was wrong. Even Albert Einstein did not believe himself. He thought he was wrong and he changed his theory. So it's just like when, for example, let's say you know the answer to a question, you have a maths problem and you already know the answer, you can write these steps, correct? You can fill in these steps when you know the answer. So this is what happened with him, that he knew the answer. I mean, he was a firm believer that steady state theory is correct. So even though his calculations, while he was working on his theory of relativity, although his equations, his calculations, they showed that the universe should be expanding, He thought that he was wrong. So he changed his equations. He changed his equations to make the universe steady again. But then came another scientist almost 11, 12 years later, and this scientist's name was Edwin Hubble. Now, Edwin Hubble independently proved again that the universe is expanding. Albert Einstein also read about this, about the theory that was given by Edwin Hubble, and Albert Einstein almost lost his school, and he said that this is the biggest blunder of my life. So that I could have been the one to prove that the universe is expanding, but because I did not believe in myself, I changed these equations, and now I am not the one. I am not the scientist who holds the discovery of expansion of the universe, but rather it is Edwin Hubble. So Edwin Hubble basically proved it independently that the universe is expanding, and Einstein called it it's his life's biggest blunder. There are even documentaries that have been made on it. If you go on YouTube and search for Einstein's biggest blunder, you'll find that there are documentaries that have been made on it. So so now Edwin Hubble established that okay, fine, the universe is expanding. Later, what we discovered was that it's not only that universe is expanding, but rather the universe is expanding in an accelerated manner. Now, what do we mean by accelerated manner? A normal expansion would be like this. This, I would say, is a normal expansion. All right. This is an accelerated expansion. This kind of expansion is an accelerated expansion. So initially we understood that universe is expanding, but later it was discovered that not only it is expanding, but it is expanding in an accelerated manner. Now for this expansion, rather let's say for any kind of work to be done, you need energy, correct? For any kind of work to be done, you need energy. So even if expansion of the universe is happening, there must be some kind of energy behind it. There must be some kind of energy that is leading to the accelerated expansion of the universe, correct? What kind of energy it is, we don't know. We have no clue about what kind of energy it is. Hence we named it as dark energy. So what is dark energy? Dark energy is the kind of energy that is leading to the accelerated expansion of the universe, but we don't know in what form. We don't know what form of energy it is. It is an unknown form of energy leading to accelerated expansion of the universe. So this kind of expansion, accelerated expansion of the universe. Now how do we know about accelerated expansion? When we look at these galaxies. So when you look at these galaxies, for example, they are moving apart like this, correct? They are moving apart like this. So it's not only that the edge of the universe is expanding, the entire universe is expanding. All right, the entire universe is expanding, and this is basically what we observe about the universe. And the energy that is supposed to be behind uh, uh, the behind the accelerated expansion of the universe, we can say that this is dark energy. So that's why dark energy is an unknown form of energy which is hypothesized to permeate all of space, tending to accelerate the expansion of the universe. So this is basically how we come to a conclusion that there is something called as dark energy, right? There is something called as dark energy. This is where we understand this from. And we are saying that almost 68% of the entire universe is nothing but dark energy. Understood? So dark energy, this is how we know that dark energy exists. Now there is another concept, and this is the concept of dark matter. So in one line, what is dark energy? The energy that is leading to accelerated expansion of the universe. The unknown form of energy, the unknown form of energy that is leading to the accelerated expansion of the universe is called as dark energy. Clear? Coming to dark matter, so what we are saying is that almost 27% of the universe is nothing but dark matter. Now, first and foremost, what do we understand by dark matter, and how do we know that dark matter exists? So first and foremost, how we understand, we say that it is a mysterious non-luminous substance making up vast majority of matter in the universe. Now, how we understand this is that, let's say, when we are observing a galaxy, all right, we let's say if we are uh, observing the galaxy, so any galaxy, all right, so in that galaxy we see that there are certain planets, there are certain stars, there are other celestial bodies, etc. So depending on what we have observed, depending on what we see, let's say we see that this entire galaxy should weigh, suppose 2000 kg, it should have a mass of 2000 kg. But then when we calculate the things, depending on the observations of the movements and the gravitation, etc., we see that the mass should be much more than that. The calculations are saying that the mass should be 5000 kg, but what we are seeing right in front of us is just 2000 kg. So then in that case, where is that to 3000 kg going? There is some extra mass that we can calculate, but we can't see it. So that kind of matter that should exist but we can't see it has been called as dark matter. Just imagine, let's say, in your room, for example, all right, in your room, you have desk, chair, uh, maybe many books, maybe uh, other things of your personal belongings. So maybe you have all these things. So let's say you take everything one by one and you keep weighing them, and you have weighed everything. I mean, even let's say the walls that you have in the room, you have weighed everything. So let's say everything combined together comes out to be 1000 kg. And then after that, you pick up the entire room as a whole and you weigh it, and you find that it is not 1000 kg, but it is 2000 kg. This is what is happening with you. That there is, when you are looking at your room, this is what is happening in your room, that there are things which are unknown. There are things that you can't see in your room, but perhaps they exist in your room, right? So this is what becomes dark matter. This, for the universe, is what becomes dark matter. The unknown form of matter, the things that we can't see but we know that they exist, they are called as dark matter, right? This is how we come to understanding of the dark matter. So that's why, let's say, this is what we are seeing. So basically, let's say perhaps there are others who are also sitting and they're also enjoying the class, just that you can't see them, but they exist. I hope not, I mean, I hope not. But if at all that was true, then in that case, this is what dark matter is. So for the universe, at least, this is what dark matter is, that there is matter that we can't see but we can calculate. We understand that dark matter exists because of this, that our calculations show that the mass that we have observed is actually much less than the mass that we have calculated. So that basically accounts for dark matter. So dark matter, what we say is that it does not interact with baryonic matter. So when we say baryonic matter, baryonic means the normal matter. Baryonic means normal matter. The matter which is made of electrons, protons, neutrons, etc., they basically are called as baryonic matter. So dark matter does not interact with baryonic matter, and hence it is invisible to us. So that's why we understand this. So scientists are confident that it exists because of the gravitational effects that it appears to have on galaxies and the galaxy clusters. So that's why we understand from all these perspectives that this perhaps is something that exists, just that we can't see it. There is something called as, this is in your current affairs, weakly interacting massive particles. Weakly interacting massive particles, we call them as WIMPs. So these WIMPs, they are supposed to be the most likely candidates to be called as dark matter. That what we basically believe here is that this should be matter that is just spread all over the place, and because it is just spread all over the place, the mass that you have per unit volume or in a given area is very very less, and hence it is almost undetectable for us. One of the reasons why all these things are undetectable is also because of the gravitational force, and we'll discuss more about it at a later stage when we discuss about string theory, etc. But you'll understand that this is also something that adds to it. So that's why we basically are talking about dark matter in a manner that this is an unknown form of matter that our calculations have shown, but we have not really observed them ever. Now, coming to the formation of the universe. So, understanding the formation of the universe, what we understand is that there are a lot of different theories that have been given about the formation of the universe. We have the Big Bang theory, which is perhaps the most popular, most widely accepted theory about the formation of the universe. But then, apart from that, there are other theories as well. So, for example, steady state theory. Now it has been discarded. This is a theory that basically said that everything is fixed, everything will always remain fixed, that the universe is in a steady state and it will always remain in a steady state. So now this theory has been discarded. Then there is eternal inflation theory. So eternal inflation theory basically talks about the concept of multiverse, a concept that is very famous in films, in especially in the English films. So that concept where we say that there are multiple universes and our universe is not the only universe, but rather there are multiple universes that exist inside a multiverse. So that is called as eternal inflation theory. But again, when it comes to eternal inflation theory, uh, there is no perfect scientific proof that can help us understand whether or not this is even possible. Then we have oscillating universe theory. What it says is that the universe keeps on oscillating from an expansion to a contraction, and then expansion and contraction, and so on. So, and then there is the string theory. So what is string theory and what is the big bounce, we'll have a discussion later, because these still have some kind of scientific base, and we do see that these are all they become very very crucial from that perspective. Now, the most important, the most most widely accepted the most widely accepted one is the Big Bang theory. Now, what the Big Bang theory says is that the universe was very hot and concentrated in the distant past, and ever since then, the space has been stretching and cooling. So, what the Big Bang theory says is that the entire universe, when it was born, would have been just a particle, just a very, very, very tiny particle, a particle that would have been smaller even as compared to a proton. Even compared to a proton, this would have been a very tiny particle. But then something happened in this particle, because of which a sudden expansion started in the universe. That in this particle, all of a sudden, we see that there is an expansion that happens. And with this expansion, we see that all the different types of matter, all the different forces, they all start existing independently. All right. They all start existing independently. So now we see that all these forces, all the matter, etc., they have independent existence for the first time. The And ever since then we say that the space has been stretching and cooling, because when it was very hot and concentrated, the temperature of the universe is estimated to be 10 to the power of 32 degrees Celsius. 10 to the power of 32 degrees Celsius, meaning 1 followed by 31 zeros. This would have been the temperature of the universe, and then after that it kept on cooling down from there on. So this is what the Big Bang theory basically says. Now, when it comes to the Big Bang theory, how exactly do we know that the Big Bang theory is correct? How can we say that, okay, this is how the things happened? How can we be so sure that this is how the things happened? So there are a couple of evidences that support this Big Bang theory. All right. So first one is Hubble expansion. So Hubble expansion is nothing but the accelerated expansion of the universe. The accelerated expansion of the universe is called as Hubble expansion. All right. So this is one. So now why Hubble expansion is being called as an evidence? Because the Big Bang theory talked about this kind of expansion first, and then later we discovered that something like this actually happens. That there is actually an accelerated expansion, but this was predicted in the 1960s itself by the Big Bang theory. So that's why later that it was discovered to be correct, it further solidified the Big Bang theory. Let's say if it was the other way around, that we already knew about the fact that it is accelerated expansion, and then based on that we had formulated the Big Bang theory, then the Big Bang theory would not have the kind of respect that it has today from everybody else. Correct? So this is one. Then there is this Big Bang nucleosynthesis. Big Bang nucleosynthesis is nothing but the abundance of hydrogen and helium. Abundance of hydrogen and helium. All right. So abundance of hydrogen and helium is also called as Big Bang nucleosynthesis. And this is also something that we saw, that almost 4% of the universe is nothing but hydrogen and helium. And given the fact we know so little about the Big Bang theory, about the universe, this 4% is a big number. Now coming to a very, very important thing, that is cosmic microwave background. That cosmic microwave background is also one of the evidences that supports the Big Bang theory. So how exactly do we say that it supports the Big Bang theory? Just try to understand this. So cosmic microwave background. First and foremost, what do we mean by cosmic? What is cosmic? Where do we use the word cosmic? Quickly, anyone? Yes, space, outer space, correct. Cosmos, yes. In the universe, related to cosmos. So more or less you understand this. So space related, yes, correct. So anything which is related to the outer space, anything related to the space, we say that it is cosmic. Anything celestial is called as cosmic. Then microwave. Microwave is nothing but a kind of electromagnetic radiation which is associated with heat. And then you have the term background. So this is a cosmic microwave background, meaning that this is a background made of microwaves which are visible in the space. These three pictures that you see right here in your screen, these three pictures, they are the pictures of cosmic microwave background. The first picture that you see is a picture that was taken by a probe called as COBE, COBE, and this was in 1993. So this was the first picture that was ever taken of cosmic microwave background. And then a better picture, as you can see this one, a better picture was taken later, and this was taken through another such probe called as WMAP. This was in 2006. And then we have another one called as Planck. This was launched in 2009. So we see that these three pictures, they have given us better understanding of the cosmic microwave background, meaning that this is a background of microwaves that is visible in the outer space, that is visible in the background when we are observing the outer space, something like this. That through WMAP, let's say when we are looking at the outer space, so when I'm looking at the outer space, let's say I am sitting with my telescope and I'm just looking at the outer space with something like a WMAP. So what I see is that there are so many celestial bodies, stars and planets, etc., which are there, which are visible. But in the background, I see something like this. In the background, I see cosmic microwave background. So that's why it is called as cosmic microwave background, because it is visible in the background and not visible just as a bunch of different celestial bodies. So now cosmic microwave background, again, why do we call it as an evidence? We're calling it as an evidence because this is where we understood that the universe would have been very hot and concentrated. That all of a sudden there was a sudden expansion that happened in the universe, and that's why a lot of heat, etc., would have been released. And this is what is visible as an afterglow. This is what is visible as an afterglow, and hence it supports the Big Bang theory, because this is what the Big Bang says, that all of a sudden there is a temperature that starts to fall, a lot of energy has been released, and all these things. So that is how we understand that this is basically where uh, cosmic microwave background acts as an evidence. So cosmic microwave background, cosmic microwave background also is a current affairs topic. It is also related to uh, your current affairs, also related to the Nobel Prize that was given a couple of years back in physics. So that's why cosmic microwave background is very, very important as a concept also for your examination. Because if you look at the newspaper, the Hindu or the Indian Express, you'll find that in a year there are at least 2 3 articles which are related to cosmic microwave background. All right. So we basically can say that this is a background of microwaves representing the early heat energy of the universe visible in the background. When we observe the space. So this is how we can define what cosmic microwave background is, and it is one of the major evidences that support the Big Bang theory. All right. So on the basis of these three evidences, we understand that this is how the Big Bang theory, or this is how the universe would have existed in the early part of the universe. Now, when we look at the universe, we see that there have been various phases of development in the universe, and all these names are not really important for you, that what is Planck era and what is inflationary era and what is reheating phase and so on, not important for you. But how exactly the development happened, this is something that becomes important. So just understand this, just understand how the development happened and what was happening in the early part of the universe, what was happening when the universe just had begun. So first we call it as the Planck era, starting from the Big Bang going up to just 10 to the power of minus 43 seconds. So for a very tiny fraction. So this Planck era is when you have the universe as a tiny particle, right? When you have the universe as a tiny particle, and then after that we have the inflationary era, where we see that the expansion starts. So from 10 to the power of minus 43 up to 10 to the power of minus 33 seconds, we see that inflationary era is where the expansion starts, and that's why it is called as inflationary era, from inflation. So the universe is now inflating, it is expanding. Then we have the reheating phase. Now, in the case of reheating phase, what we see is it starts from 10 to the power of minus 33 seconds up to 10 to the power of minus 10 seconds. Now, this is where we see that all the different types of particles, they start to exist. And the first particle to exist here was a quark. The first particle to exist was a quark. Now, in case of a quark, what we see is that quark became the first particle to exist. From here on starts the particle era, from 10 to the power of minus 10 up to about 10 seconds. So now what we see is that this quark now leads to two different families of particles called as hadrons and leptons. hadrons and leptons. From hadrons, the formation of protons happen. Formation of protons and formation of neutrons. They take place from here. And from the leptons, there are three types of particles that are formed. One, our electrons, and then there were also muons and also taus, TAU. Out of this, these three particles, they were stable particles. All right, these three particles were stable particles, and these two particles, they were unstable particles. They were unstable particles. So what happened then is that the unstable particles, they decayed very quickly, and they would decay into electrons. So these stable particles then finally they would combine together and lead to the formation of hydrogen. So hydrogen is then formed in the 10th second. So all these things happened just in 10 seconds. That from a very tiny particle, expansion starts, then all the forces and all the different types of particles, they start existing together. Then after that, we see that a family of particles called as quarks and also antiquarks, these are also, they start existing. All right, so there were quarks and there were antiquarks. But what happened here is there were also antiquarks. But what happened is that the number of quarks in the universe were more than the number of antiquarks. All right, the number of quarks were more than the number of antiquarks, and these are just particles. Just know that these are particles. No need to understand beyond that. That what was happening and what is exactly this particle. There were quarks and antiquarks. Now, because these were antiparticles of each other, they started killing each other. They started annihilating one another. And while annihilating one another, because the number of quarks were more than the number of antiquarks, quarks prevailed, antiquarks vanished. If the number of quarks and antiquarks were equal, if the number of quarks and antiquarks were equal, then in that case, we would not be having this class today. The universe as it is would not have even come to its existence, because every particle would have just killed one another, because the number of particles of quarks were more than the number of antiquarks. That's why we, unfortunately or fortunately, whatever you want, we have a universe today, and we have the world today. All right, so this is how the things would have panned, and then ultimately we see big bang nucleosynthesis, as we discussed, that this is how the hydrogen and helium formation begins. And then finally we come to the photon era, starting from the 20th minute up to 380,000 years, where we just see that all these things, all hydrogen keeps on combining together, keeps on forming helium, more hydrogen, more helium, all these things happen. And ultimately at the end of 380,000 years, the first star is formed. The first star comes into existence 380,000 years later, after the formation of the universe had begun. So this is how the development of the universe would have happened according to the Big Bang theory. All right, according to the Big Bang theory. Now, last thing before we take a break, what exactly is still not explained by the Big Bang? What happened before the Big Bang? What caused the Big Bang? Although the Big Bang has been able to give us an idea about a lot of things, it has given us an insight into a lot of things about what would have happened in the early part of the universe, but still does not answer two crucial questions: that what before the Big Bang, because we are starting from this particle, we are not saying that what preceded this particle, was there anything else before this particle, where did this particle come from, we are not saying anything about it. And then after that, what caused the Big Bang, that what was the trigger, that why this sudden expansion start, we don't know, we don't really know. So that's why we don't know about the answer to these two questions yet. So these are, you can say, things which have still not been cleared. These are things which have still not been given an answer to by the Big Bang theory. All right. So this is about Big Bang. Now let's take a break here. The time right now is 7:46 a.m. Shall we be back by 8? right? Let's be back by 8 a.m. And meanwhile, if you have any questions from whatever we have discussed in last 1 hour, please ask all those questions. After the break, I'll first take your questions, and then after that, we shall move forward. So meanwhile, whatever questions you have, you just keep on typing your questions so that I'll take your questions when I come back from the break. Welcome back, students. So let me just first go through your questions and then we shall move forward. About the breaks, everybody has written, there are comments which say that the break is too long and there are comments which say that the break is too short. In general, we'll take this kind of a break, 13, 14 minutes. I mean, maximum of 15 minutes, more, not more than that, and minimum of maybe 10, 12 minutes. So that should be it. I don't think we need more than that or less than this. Anyway, so reheating era and particle era, please explain. So, from the perspective of all these, just understand this, that when we are talking about the reheating phase is where for the first time the first particle started to exist. This is where the quark started to exist and all the different types of forces they started to exist. So that basically is said to be the reheating phase, and the particle phase is where all the different particles they started to come. So the hadrons, the leptons, the electrons, protons, neutrons, all these formations of different types of particles, that happened in the particle era. Hydrogen and helium were formed in which era? In Big Bang nucleosynthesis after the 10th second. How can one know that something happened at the time lapse of 10 to the power of minus 40 seconds? How do the scientists calculate such short time? See, it's all based on a lot of simulations that they have run, a lot of such experiments, and a lot of such knowledge has also come from, let's say, an experiment like the Large Hadron Collider. So that also has given them some of the insights lately. Plus, a lot of that has also been based on many assumptions about how particles work and how physics in general works. So that's why, uh, in general, I mean, as a thumb rule, what we see in physics is that physics always starts with an assumption, that we assume first and then we try to prove that assumption to be correct. And if we are able to prove that assumption to be correct, it becomes a theory or a law. And if we are not, then we try looking for something else. So this is how, in general, as a thumb rule, we see that physics works. That first we assume that something is moving, then there must be a force behind it. Then we try to prove it, that whether actually there is a force that is leading to that kind of movement. If you are able to prove it, it becomes the first law of motion. So this is how it works. So many a times what happens is that it all starts with an assumption, and then we look at the various aspects of it, trying to prove it to be correct. So, and then there are a lot of complexities that go behind the scene, where I don't think we are at a level that we should explain, we should discuss all that. If we don't know about what before and what caused the Big Bang, then how do we know that what Big Bang theory is? So Big Bang theory basically starts from there. It says that, okay, fine, if this is where we are, this is how it might have begun. And that's why it is a theory, it's not a law. Just remember this, that when we talk about Newton's laws of motion, we know that it's law because it's universal, because it's something that we know happens for sure. But when we say that it is a theory, when we say that the Big Bang theory is a theory, so when we say that it's a theory, the meaning is that it is something that we think is the most probable explanation. It might change tomorrow. We'll discuss about string theory, and how string theory can become a possible explanation tomorrow, and then the Big Bang theory might be discarded. Just how the steady state theory was one of the explanations, and now it's not. So that's why remember that it is called as a theory and it's not a law. Neutrinos and neutrons are the same? No, they're absolutely not. So when it comes to a neutron, neutrons first of all are large particles, they are heavy particles, they are found inside any given atom. So inside the atom, you might know that there is a small nucleus, and inside the nucleus you find a neutron. And the name of the neutron was given because it is a neutral particle which has mass. All right, it's a chargeless particle that has a significant mass. Neutrino, on the other hand, they are not really bound by any nucleus as such. They are not bound only by an atom. They can freely exist as well. At the same time, their masses are much lesser as compared to the mass of the neutron. it is not at all comparable to the neutron in terms of its mass. Only in terms of its charge it is comparable. The origin of the word also is very interesting, because origin of the word, for example, neutron comes from neutral. So neutral particle named as neutron, because proton and electron existed, neutron became the neutral particle. Neutrino is said to be a particle because it's a very small particle, almost a massless particle. And the origin, I mean the first discovery of the neutrinos happened thanks to some Italian scientists. And these Italian scientists, they have for anything that is very small, something that is very small, or anything that is of that scale, there is always an eno that they added to it. All right. So when you say neutrino, so if you think of an Italian perspective, if you think of an Italian dialect, so when an Italian scientist says neutrino, when they say neutrino, it means that it is a particle which has a very small mass, and hence the origin of the word actually comes from there. All right. So neutron and neutrino, they are not at all related. They are completely two different set of particles. Just that both of them are neutral particles, not carrying any charge. Unable to understand string theory. We have not even discussed string theory yet. That's the next topic. What is the best example of antimatter and heavy element? So, antimatter, positron, we just discussed. I had written it there also. Positron is an antimatter of electron. Similarly, neutrons have antineutrons, protons have antiprotons, etc. So these are all antimatter. And heavy element, every element apart from hydrogen and helium is a heavy element. Carbon, nitrogen, oxygen, chlorine, bromine, iodine, uranium, plutonium, everything, all of these are heavy elements. What is charge or chargeless? I mean, that's electrical charge. We are talking about electrical charge. For example, let's say when you talk about an electron, we know that it's a negatively charged particle, and proton is a positively charged particle. So when the number of such positive and negative charges are equal in a particle, they will become chargeless. That means neutrinos and neutrons are antimatter? No, not at all. Not at all. What I'm saying is neutrons and neutrinos are completely two different particles. They have no relation whatsoever. How can we say electrons are stable particles with regards to quarks? I mean, the explanation of this goes to particle physics, where we are talking about the fractional charges that the quarks have and the number of fractional charges that come together to form a -1 charge, where the charge to mass ratio is not so distorted that it will become unstable. In case of muons and taus, that's a very distorted ratio. That's why they're unstable particles. But I mean, these things are not really required for your examination. Yes, Chaitanya, you are correct. 1 by 3 minus 1 by 3. But not only that, plus 2 by 3 and minus 2 by 3 charges are also there. And combination of all these charges, they make up these particles. You are correct. Why Big Bang does not explain what before and after it? Because I mean, we can't say why it cannot explain. It does not explain. I mean, it has no explanation for what happened before or that, after that. It just assumes certain things, and based on that, certain things have been postulated. Right. So let's move forward. The next topic for us is string theory. Now, in case of string theory, when we talk about string theory, this is a theory, again, something that tries to explain the existence of various different particles. It also tries to explain the universe as it exists today, but in a very different form, in a very different form. And what we basically see here is that in this particular scenario, what string theory says is that all the particles in the universe, all the different types of particles, all the different types of forces, they all are made of tiny strings. It says that all of them are made of very tiny strings, and the different types of vibrations that are caused in these tiny strings, they form very different types of particles. It's almost unimaginable for us that how exactly does this happen. So just consider this as any stringed musical instrument like a guitar or a sitar or a violin, where you have certain strings, and when you play those strings you are able to produce different types of musical notes, correct? You are able to produce different musical notes based on the strings that you play, correct? So something similar is what the string theory says about the entire universe. It says that the entire universe is also made of these tiny strings like this, and these tiny strings, when you produce different types of vibrations, different vibrations produce different types of particles. Now, as of today, there is no real way in which we can prove string theory to be correct. But what we see is that the string theory, why still it has been uh, very widely discussed, and why many scientists also have accepted this and they have been trying to prove it to be correct, is mainly because if string theory is proved to be correct, then it will become a candidate for proving theory of everything. Now, understand a few things here. First of all, what string theory is saying. String theory says that the universe basically is being described here in terms of vibrating strings rather than particles. What we know about matter as of now is that matter is made of molecules, molecules made of atoms, atoms have subatomic particles like electrons, protons, and neutrons, and so on. Correct? But it says that no, even all these particles like electrons, protons, and neutrons, they are made of vibrating strings, very small vibrating strings that can be of the order of 10 to the power of minus 35 meters, which is something that we can't observe. We have no microscope or any instrument that can see at the level of 10 to the power of minus 35 meters. So we don't even know whether it exists or not. It's a theory. So what it says is that string theory, what the string theory says is that all the particles, all the particles, or rather, let me call it all matter, all the matter and forces are made of very tiny strings. Vibrations in these strings, vibrations in these strings produce various types of matter and forces. All right. So this is what the string theory says, that every particle, every force, every energy is made of these tiny strings. And when you, just like musical notes, that when you pluck the notes, or let's say when you pluck the strings differently, you produce different types of musical notes. Similarly here, when you produce different types of vibrations in these strings, they would produce different types of particles. Just know this, don't go beyond this. All right. Now, why string theory has become so popular? It has become popular mainly because it would become a candidate for theory of everything. Now, theory of everything is a very popular theory which tries to unify all the fundamental forces. See, there are few things that we are discussing here. Just understand all of these one by one. So, this theory of everything is about the unification of fundamental forces, unification of fundamental forces. Now, what do we mean by unification of fundamental forces? All right, there are certain forces in nature which are called as fundamental forces. There are four such forces. Anyone who knows the names, can you tell me which are these four fundamental forces? There are four fundamental forces. Can you name them? Perfect. A lot of you have given all the correct answers. Wonderful. So there are four fundamental forces. We have strong nuclear force. We have strong nuclear force. We have the weak nuclear force. We have the gravitational force. And we have the electromagnetic force. Let me first write electromagnetic and then gravitation. Alright, so these are called as the four fundamental forces. These together they are called as fundamental forces. Now, what is this unification of fundamental forces? Unification of fundamental forces means that we are trying to find a single equation that can govern all these forces. Right now, what we have is electromagnetic forces are different. You have formulae for all these forces, they are different. For gravitational force, the formula are different. The nuclear forces are very, very different. So, but we don't know how to combine them all. But the way we know about things, we know that there was a time when everything was one, that you had this tiny particle that contained everything. So if everything came from this one, then we must be also able to unify everything into that one. But we haven't been able to do that yet. We haven't been able to do that yet. And that is what can be made possible through the string theory. That is why string theory. That is why we are talking about these vibrations, and that is why we are talking about the string theory. Now, there is one more small concept that you should know. I know I'm overloading you with some certain concepts here. These three together, these three together, they are called as the standard model. They are called as standard model of physics. Just know this, that they are called a standard model of physics. The reason is that these three forces, they are very strong forces, and compared to that, gravitational force is a very weak force. All right, so if we, let's say, if we are trying to arrange these in terms of their magnitude, in terms of their magnitude, strong nuclear force is the strongest. Then after that comes the electromagnetic force. Then after that comes the weak nuclear force, and then after that comes the gravitational force. So this is the order. This is the order of their magnitude. All right, and here you can say that, I mean, this is very, very less. I mean, gravitational force is very, very weak compared to all the other forces. So that's why gravitational force in this universe, I mean, uh, it's very difficult to detect it. Very difficult to detect. Why? Mainly because of the fact that it's not easy that gravitational force be compared to all the other forces, and that's why when we look at the standard model, gravitational force has not been considered there. So this is basically how we know about the string theory. This is, I mean, the basic of string theory. We can't go beyond this. That's too technical for you to know. Even these things are not as easy for you to know, but still some important concepts, because very often it is also in the current affairs. Very often it is there in the current affairs. So you should know what is string theory, what are fundamental forces, what is the standard model, what is the unification of force. There's one scientist. Okay, one more question. There's one scientist whose name is always associated with theory of everything. Can you name me the scientist whose name always associated with him, with this? Yes, Janvi correct. Saloni correct. Rakshit correct. Lalu correct. Narendra correct. Pavi correct. Perfect. So many of you have given the correct answer. So theory of everything. One scientist whose name always associated with it is Stephen Hawking. So Stephen Hawking has been a scientist who almost, you can say, all his life he kept on he kept on studying about theory of everything. He tried to prove theory of everything. A large part of his second half of his life went on in just trying to explain what theory of everything could mean. So that's why his name is often associated with it. Unfortunately, one of our, you can say, one of the greatest scientists of our generation, he passed away a few years back. Could not prove it to be correct. That's why one of the greatest scientists of our generation does not have a Nobel Prize in his name, because Nobel Prize is always given when you invent or discover something, when you prove something. Unfortunately, he was working on something which is perhaps one of the most complex of the theories of our times. Not easy to prove, not easy to get away with it. So unfortunately, the greatest scientist of this generation does not get a Nobel Prize. And Nobel Prize is, first of all, also second of all, also given to people who are alive. So unfortunately, he perhaps will not get a Nobel Prize. So unfortunately, but yes, still remains one of the greatest scientists of the times. Look at this question. This was asked in your 2017 paper. The terms event horizon, singularity, string theory, and standard model are sometimes seen in the news in the context of what? Observation and understanding of the universe, study of solar and the lunar eclipses, placing satellites in the orbit of the Earth, and origin and evolution of living organisms on the Earth. I'm launching the poll for you. Please mark your answers. Wow, wonderful. 85% of you have given the correct answer. That is A. And I'll just explain it because some of you have marked B, C, and D. The terms event horizon, singularity, string theory, and standard model. We have still not studied what is event horizon or singularity, concepts which are supposed to come later. And then string theory is something that we discussed. Standard model is something that we discussed in the context of what? So observation and understanding of the universe seems correct. This is the context in which we have been studying everything until now. Study of the solar and the lunar eclipses. We have not really studied anything about the eclipses, and they are not really related to it, because eclipse is more about the shadowing of one celestial body in front of the other. So that's why this cannot be the correct answer. Placing satellites in the orbit of the Earth. It's more about gravitation. That's more about gravitation than anything else. Origin and evolution of living organisms on the Earth. We are not only talking about the living organisms, we are talking about everything in the universe, correct? So that's why this can't be the answer. So correct answer here will be A, observation and understanding of the universe. So after all the complexities about what we have studied, this is the question that they have asked in the paper. All right. So anyway, so we'll discuss about all these things. Even singularity, for example, the small particle that we were talking about, it is also called as singularity. The small particle where we say that the universe began from, it is also called as singularity. Although singularity is also a term that is used in the context of black holes that we'll discuss at a later stage. Now, So this is the first part where we understood the basics of the universe, all the complexities of the universe, what is dark energy, what is dark matter, what is Big Bang, what is string theory, and all these things. Now we come to the second part where we'll discuss about various celestial bodies. So what we discussed is that almost 3,80,000 years later, the first star was formed in the universe. All right. So now in this first star that was formed, let's try to understand what do we even mean by a star. That today we say that almost 0.5% of the entire universe is the billions and billions of stars in the universe. So it is a celestial body that generates light by nuclear reactions and is held by its own gravity. These are two essential points. One, nuclear reactions, basically nuclear fusion reactions. What we mean by fusion, we'll discuss later, don't worry. And held by its own gravity. It has a spherical shape because of this gravity. So I'll just write it out right here itself. Has a spherical shape because of gravity. Right? It has a spherical shape because of gravity. So that's why you'll see that wherever you have gravity, gravity gives a stability in the shape, and that stability is rather in the form of a sphere. Same we'll see in terms of planets as well, and many of the other celestial bodies which are round in shape or spherical in shape. That happens because of gravitation. So gravitation basically gives it the spherical shape. Gravitation basically gives it the spherical shape. So star, two important things. One, gravitation holds its shape, and secondly, nuclear fusion reactions happening at the core, at the center of the star. Now when we look at the star, first and foremost we look at the formation of the star, that how exactly does the formation of a star happen. The formation of a star, we say that it begins from a nebula. Formation of a star begins from a nebula. What is a nebula? The most widely used screensaver and wallpaper in the world. Something like this. An image like this, a lot of images like this. Just go and perhaps search it on Google or somewhere, and you will find that the images that you'll see, you'll find that these actually are very often used as wallpapers and screensavers. There was actually a survey that was conducted, and there they had found that the most widely used screensavers and wallpapers are actually the nebula images. So anyway, but that's not the definition. Of course, that's not the definition of nebula. So what is a nebula? Nebula is nothing but a region of dust and gases that are just spread in the space. All right, just a region, maybe no specific shape. Sometimes they do have a shape, sometimes they don't. So they are just a region of space, a region of dust and gases in the space. All right. What kind of dust and gases? They would have hydrogen gas. They would have other ionized gases. They would have methane. They might have ammonia. They might have helium. All these gases might be present, plus some dust particles, ice, etc. Everything could be present in that space. All right. So now, when it comes to nebula, so that's why just remember that nebula is nothing but a region of dust and gases in space, right? A region of dust and gases in space, and they look beautiful. I mean, that's the reason why they become screensavers and wallpapers. So for example, something like this, this nebula is also called as Eagle Nebula, also called as Pillars of Creation. So this is an actual image. It's not a made up image. This is an actual image of a nebula. And that's why nebula looks very beautiful. And that's why there are so many people around the world who use it as their computer screensavers and wallpapers. Now, when it comes to nebula, so we understand that it is just a region of dust and gases, various different types of gases. Hydrogen is present there, helium is present there. Now what happens is that because of certain conditions that we have in the nebula, we see that this is where the formation begins from. All right, this is where the formation begins from, that we see that hydrogen gas or let's say helium gas, etc., they would start coming together. They'll start coming together, they'll form a core. And as they form a core, they have a mass now. If they have a mass, they have gravitation. If they have gravitation, they will start pulling everything else that is there in the surrounding areas. Whatever they have in their vicinity, everything will be pulled towards this particular center. Correct. So once everything is pulled towards this center, this is where they'll have start having a mass. They will start creating a ball of mass, and this is first called as a protostar. This is first called as a protostar, and then after that we see that this protostar starts to bulge, and starts to the nuclear reaction start, because the temperature at the center is very high, the pressure exerted is very high. So because of that, we see that nuclear reactions start here, and then starts to ultimately form a star. So naturally, what we'll see is that they would form a star. All right. So this is how we see that formation of a star happens. The clouds of dust and hydrogen gas, they will collapse under their own gravity. The center of this cloud becomes very hot and nuclear fusion occurs, and this releases so much energy that stars then shine with their own light. So this is how it happens. All right. Nebula is where hydrogen is. Hydrogen will start combining together, form helium, nuclear reaction start, ball of mass is made, protostar it becomes, gravitation increases, starts attracting everything else, forms a ball of mass, ultimately converts into a star. This is how formation of star happens. Now, one very, very important concept here is about the life cycle of a star. And let me start with a question. I'm asking you a question. When our sun dies, it will convert into a black hole. I'm giving you two options, whether this is false or whether this is true. I'm launching the poll, giving you a very short time. Please mark your answers and tell me, what do you think, whether this is correct. When our sun dies, will it convert into a black hole or not? So 54% of you have said that it will not convert into a black hole. 46% of you have said that it will convert into a black hole. The answer is no. And some of you, as I see in the comments, you have already mentioned that it would convert into a white dwarf, or there is a Chandrasekhar limit, as you have mentioned. So, yeah. So, Nitesh, you are correct. Amrit, you are correct. Ilma, you are correct. So, you have given the correct answers. So, that is a confusion. And that's why I asked this question, that we have a general notion in mind, right? We have a general notion in mind that a black hole is formed when a star dies. Correct. This is something that many of us know, that a black hole is formed when a star dies. But it's not that when every star dies, it will convert into a black hole. That's not correct. Only certain stars, when they die, they would convert into a black hole, others would not. All right. So this is where we need to understand how the life cycle of a star starts and how it finishes. So every star will start from a nebula. All right. Every star will start from a nebula. So we discussed about the nebula. Now, from the nebula, two types of stars can be formed. One called as an average star and one called as a massive star. Now, what is an average star? Average star is any star that has a mass up to 1.44 times the mass of the sun. All right. I'm writing it. Stars with mass equal to 1.44 times mass of the sun. Correct? Our sun. So every star. So for example, let's say if you consider our sun's mass to be 100 grams, then any star which is having a mass up to 144 grams will be called as an average star. Now, what happens to an average star? It first converts into a red giant. A red giant is a star which has a big size but a very low temperature. So it converts first into a red giant, then it converts into a planetary nebula. Now just understand this: planetary nebula has nothing to do with a planet, just that it is a round shaped or disc shaped nebula. That's why it looks like a planet. That's why we call it as a planetary nebula. Otherwise it has nothing to do with a planet. So from planetary nebula, ultimately a white dwarf is formed. So what happens to an average star? That it converts into a white dwarf. All right. So when our sun dies, it will not convert into a white dwarf. Sorry, it will not convert into a black hole. It will convert into a white dwarf, because our sun is an average star. All right. Our sun is an average star. And then you have massive stars. So massive stars are the stars which have mass more than 1.44 times the mass of the sun. They would first convert into a red supergiant. Then after that, there is something called as supernova. Remember we discussed that neutrinos, the natural source of neutrinos is supernova. What is supernova? Supernova is an explosion at the core of a red supergiant when it becomes extremely unstable. All right. So explosion at the core of a red supergiant when it becomes extremely unstable is called as supernova. So supernova is nothing but an explosion. All right. Explosion that happens at the center of the red supergiant, and because of this explosion, a lot of neutrinos are released. So they are said to be the largest source of neutrinos in the universe. All right. They are said to be the largest source of neutrinos in the universe. So after supernova, what happens? Either a neutron star will be formed or a black hole will be formed. So here also there is no guarantee that black holes will be formed. Black holes may be formed here. All right. And neutron stars, just remember, these are the smallest stars. These are the smallest stars in the universe. So either a neutron star will be formed or a black hole will be formed. When would a black hole be formed or when would a neutron star be formed? It's very difficult to say. There is no real limit here, as we have between the average and the massive stars. We don't really have a limit here between the neutron stars and uh, the black holes. But generally speaking, what we see is that black holes will be formed when a massive explosion happens and you have a larger region. Then there are higher chances that black holes will be formed, and for a smaller massive star, perhaps neutron stars will be formed. But still it is very difficult to say because we don't really have a lot of data here, and a lot of observations have given us various different types of results. So ultimately this is where we see. So this is how the things are, and this is what the life cycle of a star looks like. Look at this question. This was asked in your 2009 paper. Who of the following scientists proved that the stars with mass less than 1.44 times the mass of the sun end up as white dwarfs when they die? I'm launching the poll for you. Please quickly mark your answers. Great. So 57% of you have given the correct answer. Let me just discuss this with you once. So this number, this basically was proved by an Indian scientist, S. Chandrasekhar. And that's why this number, if you have heard of something called as Chandrasekhar limit, this number is also called as the Chandrasekhar limit, because he was the one to prove it first, that if you have a mass less than 1.44 times the mass of the sun, then in that case these kind of stars will end up as white dwarf and black holes won't be formed in these kind of cases. So he was the one who proved it, and that's why this number was named after him, and now this number is called as Chandrasekhar limit. All right, so this is how the concept of Chandrasekhar limit comes from. Now we are talking about black holes. So when we are talking about black holes, just remember one thing when we talk about the black hole, that black holes basically are formed when a massive star dies. All right. Now, when we say that a massive star dies and it converts into a black hole, understand the meaning. There are two words here: black hole. So why do we say that it is a black hole? Why black? First of all, why black? Black because of absence of light. All right, absence of light. So uh, when the star dies and the supernova happens and the black hole is formed, black hole has a very strong gravitational field. The center of a black hole has a very strong gravitational field, and because of this strong gravitational field, anything that comes around this black hole will be pulled towards this black hole, will fall towards this black hole, so much so that even light particles cannot escape it. So what happens is that the light particles, which are also called as photons, if these light particles come in the surrounding areas of a black hole, then in that case they will fall into the black hole. They will fall into the black hole, and that's why this area is constituted by an absence of light. There is no light in at the center of this black hole. All right, at the center of the black hole, you don't have any kind of light, and that's why it is called as black. Second term is hole. Why hole? Because it is like a well, or more like a funnel, you can say. Just let's say if you imagine a well, generally speaking, what you'll see is that all the wells would have a boundary. Correct? There will be a boundary that at least signifies that this is a well here. And what happens if somebody crosses the boundary? You fall into the well, right? Don't try this at home, but if it happens, you fall into the well. So something happens here as well, that there is a boundary. There is a boundary of this black hole as well, and if any particle, any object, any celestial body, it crosses this boundary, then in that case it falls into the black hole. That's why we are saying that it is more like a well, it is more like a funnel, where we see that something like this happens. This boundary is also called as event horizon. This boundary is also called as event horizon, and the center of this black hole is also called as singularity. Right? Center of this black hole is also called as singularity. So what happens here is something like this. If you look at this figure, this is how a typical, this is what a typical black hole looks like. So this is where you have event horizon, right? This is where you have event horizon. So anything that has not crossed the event horizon, it perhaps will be safe and it will not fall into the black hole. But once any particle, any object, any celestial body, anything, if it crosses the black hole, if it crosses the event horizon, then in that case it just falls at the center, towards the center of this black hole, towards the singularity. and this singularity, it has a very strong gravitational field. It has a very strong gravitational field. All right, it has a very strong gravitational field, so that's why all these things will simply fall at the towards the center of this black hole. So this is basically what happens. All right, this is what will happen in a given black hole. That's why black and hole. Why black? Because of absence of light. Why hole? Because it has a shape like this, and it's like a well that if you cross the boundary, you simply fall towards the center of this black hole. Now this picture that you see here, this picture is the first picture ever taken of a black hole. This was taken by uh, something a telescope called as the Event Horizon Telescope. This picture was taken with the help of Event Horizon Telescope, and this image was taken in 2019. So until 2019, we did not really have a picture taken of a black hole. We only knew about certain things about black hole, but we had never taken a picture. And if you look at the the images of black hole before we actually had the first picture taken, you'll see that very beautiful images are being portrayed. The impression, the artist's impression of a black hole looked very different from this. It's, you can say, the difference that we have between a picture that we have taken with the help of Instagram filters and the picture that appears in your Aadhaar card. So that's the kind of picture, that the difference that we have here. This is more of an Aadhaar card picture, and if you see the images that we imagined of a black hole, you'll see that these are very different, right? You'll see that these are very different pictures, very beautiful looking pictures. If you can just go on Google and just search for black hole pictures, you'll find very exquisite pictures that they would portray. But ultimately, all our impressions of the black hole came down falling once we took the first picture of a black hole with the help of this Event Horizon Telescope program. Right? So now this Event Horizon Telescope program was a very special program that was designed to take the picture of a black hole. Now this telescope program was not a single telescope. All right. Event Horizon Telescope is not one telescope, but rather a set of 8 different telescopes that have been kept at various parts of the globe. Some in Europe, some in North America, some in South America, like this. So we basically have taken all these telescopes together, and together they form a very big aperture. All right, together they form a very big aperture. Now aperture basically is nothing but an opening. For example, your cameras also have an aperture. The bigger the aperture, the better are the chances that it would be able to take pictures in very low light as well. Aperture basically is nothing but an opening. In your cameras, in your mobile phone cameras also, you'll see that they have an opening. If they can make a bigger opening, it makes means that they will let more light come into the camera, and then in that case, even in very low light conditions as well, they'll be able to take a picture. So this is what we try to do here as well, because a single telescope would never have a very big opening, but all these telescopes combined, they formed an aperture, you can say, in a manner which are of the size of the earth itself. So very big aperture, meaning that even the smallest uh, or the tiniest fractions of the light particles that we could capture, we would be able to capture. And that's why we were able to take a picture of a black hole with the help of this Event Horizon Telescope program. So that's why Event Horizon Telescope program became very, very popular, because first it had taken a picture of a black hole called as M87, black hole called as M87. So what are black holes? Places in space where the pulling force of gravity is so strong that even light cannot escape, right? So these are very small in area but very massive. So that's why you can say that density is very high, correct? They will be very dense areas. What is density? Mass by volume. So mass here is very, very high, volume is very, very low, so density is very, very high, correct? So, and they have extreme gravity. For the first time, with the help of Event Horizon Telescope program back in 2019, we took the first picture ever of a black hole. This was M87. And then after that, later, we have also taken the picture of Sagittarius A star, which is a supermassive black hole which is at the center of our own Milky Way galaxy. All right. This M87 is called as M because of Messier. This is Messier 87 star. So this is the black hole, the first picture that was taken. And then we have also taken the picture of the Sagittarius A star later. So now there are two different pictures of two different black holes that the Event Horizon Telescope program has now taken. All right. So this is what we know about black holes. This is what we know about the black holes. These are some of the key facts about black holes. Now, there is one more concept related to these things, and this is the concept of gravitational wave. Now, what do we mean by gravitational wave? Gravitational wave as a concept, I mean, it is a wave that should have gravitational origin. That's why we are calling it as a gravitational wave. Now, what do we mean by gravitational wave? And where is the origin of this gravitational wave? Gravitational waves were first predicted by Albert Einstein. Back in 1915, he had predicted the presence of gravitational waves, and it took us almost 100 years to prove the existence of gravitational waves. So that's why we are talking about this, that that he had figured out almost a century ago that waves should exist without the help of any technology, all the advanced technologies that we have today. And then 100 years later we were able to find it, and in 2014 a Nobel Prize was also given for the discovery of gravitational waves. All right, for the discovery of gravitational waves. So what are gravitational waves? So when we are saying that these are gravitational waves, means that these should be waves which are gravitational in origin. So what do we mean here? Why do we have waves which are gravitational? How are they gravitational waves? So we are saying that these are ripples in space time. Existence was predicted by Albert Einstein back in 1915, caused due to violent and energetic events like colliding black holes, supernova, colliding neutron stars, etc. Understand what is happening here and how exactly do we get gravitational waves. All right, how do we understand what gravitational wave is? Look at this picture. In general, when we think of the space time, we imagine the space time to be like a mesh, like a net, what you see on the screen right here. So this mesh is just like, let's say, imagine a football goalpost. All right, imagine a football goalpost. So what happens on a football goalpost? That if you, let's say, kick a football towards it, what happens? That as soon as the football hits the net, ripples will be formed in the net, right? Waves will be formed in the net. So this basically is what we basically see in the space as well. Any object, any celestial body which is very massive will create more waves. Just imagine, there are two types of football. Let's say there is one football which is very light in weight, maybe made of plastic, very, let's say, lightweight plastic. All right, you, let's say you kick that football towards the football goalpost. So when it hits the net, ripples will be formed, but these ripples will not be very strong, very massive ripples. Let's say there is the other football that you have. There is a football which is made of iron, and you take this football made of iron and you kick it towards the football goalpost. What will happen? First, you will break your leg, and then when this football hits the goalpost, the wave that will be formed here, this wave will be very violent, right? This wave will be visible, correct? So so what happens here is that the ripples that you are forming because of that, these ripples will be very strong ripples, very violent ripples. Same happens in the space. A normal celestial body, a small celestial body, let's say like the Earth in the context of the universe is very small. So that's why Earth will not cause a ripple which is very strong, which is very massive, and which is something that can be observed easily. Any planet for that matter, or even a single star, cannot form a ripple which is so strong that you'll be able to observe it. But when you have something which is very violent, when you have something which is very massive, collision of stars, collision of galaxies, merger of galaxies, a merger of black holes, collision of black holes, supernova, these kind of events, these are very energetic, these are very massive. So that's why, or even the birth of the universe itself. So all these are very massive events, and when you have these massive events, the gravitational waves that will emerge from here, they will also be very strong. They will also be something that you can observe very easily. So that is where the concept of gravitational wave comes from. So we are talking about ripples in the space time which will be caused because of very massive events, violent and energetic events like colliding black holes, supernova, etc. So that is what gravitational wave is. So gravitational wave as a concept was first established or predicted by Albert Einstein 100 years back, and then 2014 a Nobel Prize was given for the discovery which happened just a couple of years before that. 2011 we had kind of confirmed that gravitational waves exist. So this is something that happened, and that's why, I mean, going back to the discussion that we did when I told you about the strategy for this examination, gravitational wave as a concept, the number of questions that have come before 2014 versus the number of questions that have come after 2014. Do you know how many questions after 2014, 2014 to 2023? There are at least three questions which are directly related to gravitational waves. Last 8 9 years, three questions. How many questions before that? Zero. Why? Because as a concept it existed, we had not proved the existence. So we proved the existence, it became a phenomena, questions were asked. Before that, it was just a research, questions were never asked. This is how you have to prepare. This is what you have to prepare for. Anything that has become a phenomena, anything that is new, anything that is being discussed by the scientific world, that is something that's important for you from examination perspective. All right. So this is how gravitational waves also become important for you. So gravitational wave, the existence, the that we proved, it was done with the help of laser interferometer gravitational wave observatory, or LIGO. This is an observatory which led to, and this is how it looks like, what you see right here. This is what it looks like, and this is where it was detected for the first time. India is also working on its own gravitational wave observatory called as LIGO, Indigo LIGO, right? So with the help of LIGO, we are making our own, and this has been named as Indigo LIGO. Very recently also it was in the news because now the government has also sanctioned the budget for working on the Indigo project just a couple of months back. In the month of May, I think it has been finally sanctioned. Although, I mean, principally it was accepted as a proposal back in 2016 itself, but just a couple of months back, the government of India also has given it some money, some budget, so that we can start working on the creation or the making this observatory in India. So that's why gravitational wave observatory, and this is what in India also it is being done. Look at this question. This was asked in your 2019 paper. Recently, scientists observed merger of giant black holes billions of light years away from the Earth. What is the significance of this observation? Higgs boson particles were detected, gravitational waves were detected, possibility of intergalactic space travel through wormhole was confirmed, and B, it enabled the scientists to understand singularity. So you have these four options. I'm launching the poll for you. Please mark your answers. Yeah, please mark your answers. Yeah, wonderful to see. 74% of you have marked B, which is the correct answer. Now, let me just explain still that what exactly is the answer and why we are marking B as the correct answer here. So recently, scientists observed merger of giant black holes billions of light years away from the Earth. What is the uh, significance of this observation? First is Higgs boson particles were detected. See, Higgs boson particles are very small particles. These are force particles, nothing to do with black holes at all. Nothing to do with black holes or merger of black holes at all. So that's why it can't be correct. It has no context in this question. Gravitational waves were detected, can be correct. Okay, let's hold on to this. Possibility of intergalactic galactic space travel through wormhole was confirmed. This was confirmed in the movie Interstellar, but beyond movies, it has never been confirmed. It still remains a science fiction concept. So this is wrong. It enabled the scientists to understand singularity. I know that some of you would have a confusion here because you see black holes, you see singularity, you think that these two are related. But what actually has been asked is about merger of giant black holes. Merger of giant black holes. Whenever merger of giant black holes happen, without a doubt, gravitational waves will be formed from there, right? Merger of giant black holes is a very massive event. So if it is a massive event, without any exception, gravitational waves will be formed. All right, gravitational waves will be formed. So that's why the correct answer here is this, B. So although if you see, this was a current affairs question, this is a pure current affairs question. This happened in December 2018. That merger of giant black holes led to formation of gravitational waves which were detected by the scientists on the Earth. So but even if you don't know that current affairs, still you can answer the question, correct? And if you'll observe that it is true for many of the questions that come in science and technology, where the context of the question is in current affairs, yet you many a times do not need that current affairs. If you know the concepts well, if you know the background of the concepts, many of these questions can be solved very easily even without knowing the current affairs. And same holds true here as well, that gravitational waves were detected. So correct answer here will be B. Now coming to the sun. Now sun also is a star, correct? But it's our own star, the star which holds the entire solar system together. Now when we talk about the solar system and the sun, we know that sun is at the heart or the center of the solar system, also called as the main sequence star. Just remember that all the average stars are called as main sequence stars. All right. Now, when it comes to the sun, just understand some of the basics about the sun. That we have the sun divided into all these regions. You have the core, you have the radiative and the convective zones. Then you have the photosphere, then you have the chromosphere and the corona. So, first and foremost, we have the core. Core is the center of the sun. All right. This is where you have the core, as you can see in the picture. This is where you have the core. So core is at the center of this sun, correct? Center of the sun. This is where all the nuclear fusion reactions are occurring, correct? This is where the fusion reactions are occurring. So in a manner you can say that this is where all the heat and light of all the heat and light is being generated, correct? All the heat and light is being generated here. So overall what happens is that it becomes a source of all the heat and light that you have in the solar system also. So everything comes from here. So core is where the fusion reaction occurs, correct? Fusion occurs here, and that's why it has a very high temperature. Temperature can be as high as 15 to 20 million degrees Celsius. 15 to 20 million degrees Celsius could be the temperature of the core, because nuclear fusion reactions are occurring at a very large scale, and hence it has a very, very high temperature. Now from here on, all these particles and energy, they are emitted outward. They are emitted outward through the radiative and the convective zone. Through the radiative and the convective zone, all these energy particles and all these particles, plasma, etc., they keep on moving outward. Then you have the surface of the sun called as the photosphere. Now, of course, now we have come away from the center. We have come away from the source of heat. So the temperature keeps on decreasing as you come out of the core of the sun. And here you will find that at the photosphere or the surface, the temperature could be in the range of 5500 to 6000 degrees Celsius. 5500 to 6000 degrees Celsius could be the temperature of the surface of or the photosphere. Right? Then after that, we have the atmosphere of the sun, where it is divided into two parts called as the chromosphere and the corona. Now, when we look at the chromosphere and the corona, just understand this, that these two, they together form the uh, these two together, they form the atmosphere of the sun, correct? They form the atmosphere of the sun. Now here, since we have come away from the center, since we have come away from the core, away from the source of all the heat and light, temperature should have further decreased, because from 5500 degrees Celsius you should have come down. But what we see is something different. What we see is that in chromosphere, the temperature could be as high as 50,000 degrees Celsius. The temperature could be as high as 50,000 degrees Celsius, and in the corona, the temperature can be in the range of or even more than 1.5 to 2 million degrees Celsius. So, although we have come away from the source of heat, we have come away from the source of all the nuclear fusion reactions that are happening on the sun, yet what we see is that the temperature rises after you have come out of the sun, after you have come away from the sun. Why does this happen? Thankfully, we don't know. The good thing is that we still don't know. There are a lot of theories that why exactly something like this should happen, but we still do not really have a confirmation that this is exactly why this happens. Although this is something that we have been trying to study, there have been various missions. There has been this Parker solar probe that was sent a few years back, and then we have our own upcoming mission, which most probably will be launched in the first week of September, 2nd or 3rd September, I think they have given as the date, is Aditya L1 mission. So Aditya L1 mission, one of the key objectives of the Aditya L1 mission would be to find why exactly this happens. So after that, perhaps we'll be able to explain it with the help of the data that we get from here. But as of today, thankfully, we don't know why exactly this happens. That why does the temperature start rising? We have a lot of theories about it, but it's just theory. We still do not have a confirmation. We do not have a proof that this is why something like this happens. All right. So what we know is that the temperature first decreases and then again it increases as we first come out of the sun. All right. So first from the core to the surface, the temperature decreases, and surface to the atmosphere, again it increases back. So this is about all the regions of the sun. Now, related to the sun, we see that there are various concepts, and these concepts are also very, very crucial sometimes. So we'll try to understand what do we mean by a sunspot, what do we mean by a solar flare, and what do we mean by solar winds. What do we mean by the concept of these three phenomena that we often observe on the sun? Now, when it comes to these three concepts, all right, when it comes to these three concepts, understand the concept that what is sunspot, what is solar flare, and what is solar wind. If you look at the first picture, this is the picture of a sunspot. This is how what sunspot looks like. This is what solar flares look like. This is a typical solar flare, and these are the solar winds. All right, these are the solar winds. So what do we mean by sunspot? What do we mean by solar flares? And what do we mean by solar winds? Just understand this. If you observe closely, what you see is that there are these spots, right? And also remember that these are concepts which are very often in the news. I mean, every week you will find that there is one news on sunspot, or there is one news on solar flare or solar wind every week. So it's not even a concept that is in the news once in a while or once in a year, or we saw that 2 years back and so on. No, this is a concept. These are concepts that you'll find that it is in the newspaper almost every week. So understand what exactly do we mean. First, sunspot. So do you see on this picture that you have certain spots that you can observe on the surface of the sun? These are called as sunspots. Now when it comes to the sunspots, they are some things that appear as darker regions on the surface of the sun, right? Darker regions, as you can see that these are appearing as darker spots on the surface of the sun. Why darker spots? Because these are areas that have a lower temperature as compared to the surrounding areas. As compared to the surrounding areas, these have lower temperatures. And since they have lower temperatures, hence they appear as darker spots. Now, why lower temperature? They have lower temperatures because of certain phenomena. For example, many a times, a lot of particles, a lot of heat containing particles, they are ejected out of the sun. And as they are ejected out of the sun, they leave behind a vacuum. They leave behind a vacuum which has a lower temperature as compared to the surrounding areas, and that is the reason why it appears darker, because all of a sudden a lot of particles have just escaped from the surface, and as these particles escape from the surface, they leave behind darker spots. They leave behind darker areas which have lower temperature. The temperature could be in the range of 3500 to 4000 degrees Celsius. All right, so that is the reason why we observe a sunspot. So in case of a sunspot, this is what we know, that these are dark, cooler areas that appear on the surface of the sun, and they are caused by intense magnetic activities in the sun's photosphere. The sunspot could have a temperature between 3500 to 4500 degrees Celsius. What we discussed is, generally speaking, the temperature of the surface of the sun will be in the range of 5500 to 6000 degrees Celsius, and here you have a temperature range between 3500 to 4500 degrees Celsius. Then after that, what we see is that these magnetic field lines, they would poke through the surface of the sun's surface of the sun, and while they do that, this is where we see that they will lead to a lower temperature. All right, they will lead to a lower temperature, and hence we see that this sunspot will be formed. So now one thing that we observe about the sunspot is that if the sunspots have appeared here, let's say the spot that you see on the sun here, what we see is that it's not a random phenomena. It's not that randomly they have appeared. What we see is that every 11 years, if the sunspot has appeared here today, 11 years later, at the same spot, sunspots will appear again. In the same area, they'll appear again. So that's why we say that these are cyclic phenomena, and this is called a solar cycle. There is an 11-year solar cycle that is followed by the sun, and the sunspots also follow this 11-year solar cycle. All right, so that's why we see that they undergo cyclic changes which are known as solar cycle that lasts around 11 years. So just meaning that they appear at the same spot every 11 years. All right, so this is what we see with sunspot, that they will have a cyclic nature, that wherever they have appeared, They will come back. They'll come back again after 11 years. So this is what we know about sunspot. The next concept is the concept of a solar flare. Now, if you see solar flare, what you see is that these are like flames that are coming out of the sun, correct? These are flares or flames that are coming out of the sun. If you look at the scale of the earth, you can see that the earth is so small. The earth compared to the scale of the solar flare is so small. And solar flare is something what we see is that solar flares can have an impact on the solar system as well. It can have an impact on the earth itself also. And very often you'll see that there is a news, very frequently you'll see that when the next solar flare is happening, what will that next solar flare do, a strong solar flare is about to reach the earth. All these kind of news articles, we'll see that you'll very often it is there in the newspapers. So that's why understand what solar flares are. So in case of solar flares, what we see that these are big explosions. These are big explosions that happen at sun's surface, and they appear at the outer they appear or occur at the outer layer of the sun called as the corona. Now understand this that when it comes to solar flare, all right, solar flare, we are saying that these are big explosion. These are big explosion, and a lot of energy and radiation is released here. A lot of energy and radiation, which also includes X-rays and ultraviolet light, etc. And charged particles also sometimes can also be released here. Now, what happens in case of solar flare is that it is a sudden explosion. It is a sudden explosion, and a lot of energy is released. It is a sudden explosion, and a lot of energy is released from here. And depending on how much of energy is released, we see that it may have an impact on the earth also, because a lot of magnetic particles are also being released, a lot of charged particles are also being released. So because of that, we'll see that it will also have an impact on the earth. Now, why exactly solar flares are happening? Because suddenly these are happening because of some abnormality. You can say that some because of some abnormalities that we have on the sun, because of some abnormalities or some kind of uh, problems that we see in the surface, some anomalies that we see on the sun. Because of that, it happens. So that's why these are sudden burst of energy. Just remember this: these are sudden bursts of energy. These are sudden bursts of energy, and they can even have an impact on the earth. What kind of impact? They can impact anything that is magnetic, anything that is electrical, or that is electronic in nature. So for example, let's say even powerhouses, power stations can be affected, our satellites can be affected, any communication system can be affected. And they also cause something called as auroras or aurora borealis. So solar flare, they can also create beautiful auroras. Do you know what do we mean by aurora borealis? Have you heard of this term? Aurora borealis. Heard of this term? Yes, northern lights, correct. Right. So what exactly do we see here? That you'll see that they are beautiful green colored light there that you will see in the north polar areas. Right, in the north polar region, you will see that in the night sky, beautiful green colored light is visible. So that green colored light is often visible because of solar flares. And if solar flares are very strong, then these green colored lights will not only be visible in the polar areas, but also in the temperate areas as well. This year, it was in the news, I think in the month of April, it was in the news when even in Ladakh, as low as Ladakh, although normally we see in the polar areas, in Ladakh, we had for the first time observed very beautiful auroras. Heard of this news? Have you seen this news in the newspapers? Yes. So this happened for the first time. This happened for the first time, that even in Ladakh. Unfortunately, I could not visit it. I was supposed to be in Ladakh at that point of time. I had even booked my tickets, but I could not go because of some other commitments. I had to cancel my trip. I feel very unfortunate that I missed on it. Otherwise, I could have been there at the time when it was observed. such is life, can't do anything. So aurora borealis. So when we talk about aurora borealis, aurora means what? Aurora is associated with colors, right? Aurora is associated with colors. And borealis, why the term borealis? It comes from the boreal region. What is the boreal region? Boreal region is the north polar region. For example, in geography or in environment, you will study about boreal forests. So boreal forests are the forests which are found in the north polar areas. So polar areas in the northern hemisphere. So though they are called as boreal. So from there, borealis as a term has been derived. So that's why aurora borealis, because green colored light in the northern hemisphere. So that's why the name aurora borealis has been given. Similarly, in the southern hemisphere, we observe something called as aurora australis. Why australis? Because it is in the southern hemisphere near Australia, hence the name aurora australis. So these phenomena that we observe, um, a very big reason for that is solar flare. So just remember that solar flares can affect anything electrical, electronic, or magnetic. All right, anything electrical, electronic, or magnetic can be affected. So let me write can affect. They can affect anything electrical, electronic, or magnetic in nature. And that's why you'll see that in the news also sometimes it is mentioned that, for example, for New Zealand, it was mentioned in the news that power outages happened in New Zealand because of solar flares. So that's why anything electrical, electronic, or magnetic, that's why your satellites, your communication systems, your power systems, everything could be affected by solar flares if they are strong enough. And then we have solar winds. Now, in case of solar winds, they are continuous or constant flow of charged particles. All right. And primarily, they are composed of charged particles like protons, electrons, etc. And they also are emitted from the outermost areas of the sun. Now, in this scenario, what we basically see is that, just remember this, that the basic difference, although the charged particles are also coming from solar flares, the same charged particles are also coming from the solar winds. Where's the difference? The difference is that this is a sudden burst of energy, whereas in case of solar wind, these are continuous flow. This is a continuous flow of energy. That's the basic difference. All right, that's the basic difference between solar wind and solar flare. They could have the same kind of particles. All right, they could have the same kind of particles, they could have the same kind of effect, but one is a sudden burst of energy, one is a continuous flow of energy. That's the basic difference between solar flare and a solar wind. All right, so that's why you can see that solar winds are like this, and because solar winds are magnetic in nature, that's why uh, they can also have the same effect. And that's why just remember that they also can, here we'll write, can affect anything electrical, electronic, or magnetic in nature. And they can also form auroras. They can also lead to auroras. All right, so just remember that this can happen in the case of solar winds as well. Look at this question and we'll end our session here. Read this question and then I'll launch the poll for you so that you can mark your answers. 2022, this question was asked. Please mark your answers. Hmm. Wonderful. 72% of you have marked C, which is the correct answer. Let me discuss this with you. If a major solar storm or a solar flare reaches the Earth, which of the following are possible? Which are the following are possible effects on the Earth? First, GPS and navigation systems could fail. This is correct because GPS and navigation systems are electronic systems, correct? These are electronic systems. So we discussed that anything electrical, electronic, or magnetic can fail. So this is correct. Tsunamis could occur over at the equatorial regions. Now, tsunamis have seismic reasons, right? They often occur because of internal reasons inside the earth and not because of any solar flare or solar wind, etc. Correct? So, so that is why, anyway, this is not correct. So, second statement is wrong. Then, third is power grids could be damaged. So, power grids, again, this is electrical in nature. So, that's why obviously this could happen. So this is correct. Fourth is intense auroras could occur over much of the earth. Intense auroras. This is correct. I mean, UPSC would be proud that 2022 they asked this, and 2023 we saw that auroras could be seen even in Ladakh. So this is correct that this could happen. So this is a magnetic reason, you can say, in a manner, a magnetic phenomena. Forest fires could take place over much of the planet. Forest fires. So forest, if forest fires have to happen, it means that a lot of heat energy has to come. And then why only forest fires? All of us would also be roasted. So it will not only be about forest fires over much of the earth, everything will be gone. So so that's why this is not possible. Orbits of the satellites could be disturbed. Obviously it can happen. It's an electronic system, so that's why it is correct. Short-wave radio communication of the aircraft flying over the polar regions could be interrupted. This is also correct. It's about satellites, it's about electronic systems. So, yes, this is also possible. So, the correct answer here will be C. And if you could use the elimination method, you can get the answer from 2 itself because you have 2 here, here, and here. So, that's why the correct answer will be C. All right. So, let's stop our classes here. We'll begin with planets tomorrow. If you have any questions, please let me know. Let's discuss your doubts, and then after that, we shall end the session for today. Previous slide. No, this is the previous slide. How we come to know that the spot is at the same place every 11 years as Earth is moving, and even Sun is also moving in space. See, no. So it's not about Sun and the Earth moving. It's on the sun. So whether the earth moves or not, it doesn't matter. It's on the sun. So that's why it is at the same spot every time. So that's why it is nothing to do with the relative motion between the sun and the earth. How do we know that the sun is an average star? So we have defined it as an average star. We have defined it on the basis of the mass that it has. We have defined it as an average star. All right. So it's not that we know, we have defined it. We have made these classifications. I have a confusion regarding gravitational wave. You said that cause of gravitational wave are supernova colliding black holes, but doesn't every celestial body, including our Earth, emit gravitational wave? Yes, you are perfectly correct here. But what I'm saying is observable gravitational waves will always come from the things that are massive. Just as an example that we took about the football, that let's say if you have something which is very very light being kicked towards the goalpost, the waves that will come will be very weak waves. Whereas if you have a very massive football kicked towards the goalpost, you have a very strong wave. So that is where what we are saying here also. Yes, Earth will also cause gravitational wave, also form gravitational wave, but it will be hardly observable for us. That's the difference. What is main sequence? See, main sequence is nothing but when we make it's not related to your examination, but when we do the size versus mass analysis of the star, we see that we get a line like this, which is called as the main sequence. And all the average stars, they actually lie here. They always lie on the this line, and that's why this is, all these average stars are also called as main sequence stars. Not related to your examination, but since you asked. Also, the feedback forms will also be, I think, are available for you for the previous batches, and please give us the feedback. Your feedback will always help us improve further, and it's very very important for us. So please fill those forms as well. Instead of polar, if it was equatorial region, can be affected by the radio systems? No, it wouldn't be, because the equatorial areas do not have the magnetic pole. So that's why the effect of the star or effect of the magnetic winds of the sun are more at the polar regions than the equatorial regions. Leaderboard, okay, let me show you the leaderboard. Yeah, this is the leaderboard. The leaderboard is also not perfectly correct today, because the first question that I'd asked you was about where, what branch do you belong to. So that's why, I mean, many of you might have wrong answers there. So don't worry about that. So this is the list of all the students who have done well. So rank one, please send me something. All right. Once again, please explain effects of solar storm flares and spots. So sunspots will not have any effect on us. Solar flares and solar winds will have very similar effects, that anything that is magnetic, electrical or electronic in nature on the earth will be affected. So polar regions are affected, satellites are affected, aircraft could be affected, satellite stations can be affected, power stations can be affected. So anything that is electrical, electronic or magnetic in nature will be affected. Short wave, what we mean by short wave is any wave that has a wavelength that is very small. We'll discuss that later when we go to IT and communication. Aurora borealis generally observed in areas around polar regions. Why it was observed in Ladakh? Because it was very very strong solar wind, sorry, solar flare. That's why in Ladakh. Otherwise generally it will be only in the polar regions. How does it happen that going far away from the sun increases the temperature? That's what I told you, that we don't know the reason. We don't really know what is happening. We are trying to observe and trying to understand the reason behind it. Can sunspot be the result of solar flares? Very good question. Yes. They can be. Many a times we have seen that solar flares and sunspots are related. They are related to one another, and many a times sunspots can form because of solar flares. What should be my approach related to current affairs for 2025 CAC? I would say that 15 months before the examination, start taking current affairs very seriously. Until then, only the biggest of the news items is something that you should follow. Right? So let's end our class here. We'll meet back tomorrow. We'll discuss the things further. Please go back and revise everything that we have discussed today. Some of the areas are a bit complex, so that's why a revision will help. And if you have any doubts, please bring them back and we'll have a discussion on them tomorrow. Until then, thank you very much, and please go back and study. Thank you.